So everybody can hear me? Yes. Good morning, everybody. Good morning. Thank you very much for coming. I would like to welcome you all to the 21st European White Dwarf Workshop in Austin, Texas. Thank you very much for making it. So you've probably seen this poster before. This is with our LOC, SOC, and some other information. This is our website. I'm pretty sure everybody went there. If you need any additional information, it's probably still in there. Some people are still a little bit against using the word European for every single, yeah, I know that. But we also know that the European White Dwarf Workshop is a very established meeting and started in the 70s, in 74. There is one person who has attended to all those meetings. Is that right, Stefan? No.
I missed 4.
You missed 4? Oh my God, that's so disappointing. Okay, good. Okay. There you go. So now. Who? Really? There you go. So I found somebody. Hey, that's great. Awesome, yeah. So great, yeah. So there we go. So this is a series of conferences that we meet every 2 years to discuss the results and the new prospects and everything about the white dwarfs. And this year we're also hosting here in Austin. And I didn't want to change the name just because it's in Austin. We've done that in Montreal already, right? So we didn't do that recently. And we are actually also this year, we are also celebrating a lot of the former students and the new students and all the contributions that Don and Kepler made to the field. So there's a lot of us here still working on the field, and that's really, really cool. I have to say a little bit about the format of this workshop. So we're going to have 97 contributed talks. You can imagine squishing 97 talks in 1 week. It's a lot of hard work, so we're going to try to keep within 12 minutes. One of the differences that we're going to have this year is we will try to have groups of people to answer questions together. I try to make the program very similar talks, one after the other, so we can work together. Try to make it more like a discussion rather than just individual questions. But if it doesn't work, well, we can always go back to the traditional mode and see what we can do. It's a learning process. So on the news, also, we are going to have live streaming. That's why I'm holding 2 microphones. It's not because I'm so quiet. You know, that's not true. So we have live streaming there. And unfortunately, we're still, crawling into that. And it would cost a lot of money to make live streaming interactive. But one thing that we are doing is people can listen to us and they can use the Slack channel to ask questions. So this is a new feature that we have. There is a chat. There is a chat on YouTube as well, so corrected here. So here is the link. Okay, so if you sign up for the channel, somebody stayed home, please let them know that it's there, that they can follow the conference as well. And the Slack channel here. So the Slack we can use for whatever we want. Yesterday, I've seen some people doing rides, sharing rides to campus and to the venue from campus and so on. We can also ask questions. So if you can continue the discussion as the conference progresses. So if there is one talk, super exciting, and we had only 3 minutes for questions, we can keep on discussing on that over there. So that's the thing, and it's going to stay up there. So if there's a question, you can answer questions. You can ask questions, answer questions. That's another way that we can use this Slack channel. The posters are in the other room, in the Santa Rita room, where we're going to have coffee breaks. We're going to have lunches there as well. You can just walk over there, it's for us. The posters, you can pick whatever location you want, whatever stand you want to set up your poster. What else about that room? On Monday and Tuesday, we're gonna have a happy hour. So in your badge, there are 2 tickets, so 1 for each day. So, and after that is cash bar, so more than welcome. And what time? 6:30? Yes. So it's from 4:30 to 6:30, happy hour. There'll be light food and then drinks. So 1 ticket, you can sell your ticket maybe on eBay. Slack channel, yes, go for that. So just a suggestion. Okay, and the proceedings we're gonna do online so far. If it changes, we're gonna keep you guys posted. So by the end of the week, you're gonna get the template and all this stuff and all the additional information on that. Oh yes, there are some stars in your badge, right? You've seen some colorful stars as well. That is not to discriminate anybody. You are this color, you are red, you're blue. No, that's your food choice for the banquet. If you didn't get any stars, it's because you didn't sign up for the banquet. There are black stars, and the black stars are for the dessert. So just to tell you, now you know, it's a secret code for us. So take that with you on Thursday, and when you get there, you place that in front of whatever you sit, and they'll bring you magically your food choice and stuff. Okay, any questions so far? No? Wi-Fi, yes, big question. Wi-Fi, that's the code, magic code, if you want to get connected. This should work campus-wide. So if you are staying in the dorms, you can use this code. Across the street is no longer campus. It's across from Guadalupe. So just, yeah. But anywhere else, if you walk around campus, you can be connected all the time. Shall I leave that for another minute? Another second, 30 seconds? Take some pictures? Yes. Shall I smile? No. Okay. But we have here also little posters that we printed. We cannot glue them on the walls, so that's why they're not glued on the walls, but we can always bring this out on the breaks. What else? Let's see. About the boat party, yes, we should also have some fun, and this is our free afternoon activity. Boat party on Lake Travis. It takes about, so here it's, again, when you map quest something, it usually tells you, depending on traffic and stuff, so about half an hour from here. This is how the boat looks like. If you want to join, we still have some slots, not many, because there is a limitation of the number of people that can go on the boat. It's $50, and you have to pay to me today. It's not tomorrow, it's today, okay? This is the harsh deadline, because we will provide drinks and food for everybody. So today, not tomorrow, okay? It's a lot of fun. I mean, it's really family friendly. It's for 4 hours, so we go to the island, we stay around, and it's really fun. And the lake is gonna be nice. And one advantage is that on the lake, temperature is about 10 degrees cooler than here in Fahrenheit, so 5 degrees in Celsius. So it's always nicer to be on the water, but just saying, you know, if you're not convinced, no, she's not going. That's okay. I'll be there. Okay, so it's a really nice thing. Where are you? You are in Texas, just for you to have an idea of the size of Texas. Just a comparison. I'm so sorry. I didn't do that. Well, so that's just for comparison. We are in Austin, somewhere right here. And if you, well, so Texas, why we do so much astronomy in Texas, one of the reasons is McDonald Observatory. The darkest skies in the continental USA is here, and it's, you know, belongs to the university and so on. If you want to go there and visit, that's okay. Let us know. We can help you. It's just 7 hours that way, so you can go. You're more than welcome. It's okay. It's beautiful, beautiful, gorgeous. You can see the telescopes out there. It's really nice. Yeah. So Texas is pretty big. So if you start your drive in Houston and you want to go to LA, when you get to El Paso, which is somewhere here, you are halfway. And you can also flip that map. So if you go from the valley to whatever is up here, and you flip it, you know, if you would flip it, you're halfway between Mexico and Canada. So it's really big. It's not the largest state, but it's in the country, but just for comparison. Yeah, so you've all experienced a little bit if you haven't seen that already. that's where you end up being in Texas, right here. That's why it's so hot. No, I'm kidding. Yeah. Folks, stay hydrated, listen to your body, don't decide to start running. Now it's not the time to pick up jogging, running, anything like that. So don't do that in the afternoon. I joke with that. I mean, it's habitable. We know that. I mean, I raise my children here. I will survive this summer as well. But yeah, just listen to your body. If you have any issues, if you feel headache, drink plenty of water, and it should be fine. It's people survive. And one of the, I tell you, my children are here. One of the advantages is that when you survive the summer, you get to winter. And yes, this is the typical Texas storm that we have. Yes. Oh, this is chaos. You don't want to be here. School's closed. Everything is like it's. But am I lying? No, I'm not. It's really true. There's no day. This is a typical no day in Texas. But yeah. Yes, and then we go back to that summer. Anyways, if you were expecting to see some cars with those horns, decorated, or lots of cowboys, well, you came to the wrong city. And you came to the wrong time, and maybe that's not the TV show Dallas. It's a different time and so on. So Austin is very special and very unique inside Texas. So here is what we are nicknamed the Silicon Hills. A lot of industries, tech companies are moving from California to Austin area. And of course, it's for money-related reasons. But then we have a lot of companies here. And so there's a lot of tech development in town. So that is one of the aspects of Austin that makes it a little bit different. And then added to that, we are known as the live music capital of the world. So if you go to any bar downtown, and if you go anywhere, and to a restaurant, chances are that there will be live music. There are lots of festivals. So we have the tech component, and then we have the artistic component. So you mix those things together, but not only that, we are one of the largest, if not I think we are the largest university in the States. So we have like more than 50,000 students only. And then we have a lot of people, maybe 80,000 people connected to the university. In a town that has 700,000 people, it is a pretty large percentage for such a big city. It's not a university city per se, but if you put that together, so we got the students, the university, very international, we got the music, and we got the tech, so it makes it a very unique place and very nice to raise the children. So yeah, we really enjoy Austin, so I hope you also enjoy Austin as well. So that's one of the mottos that you're gonna see out there. And I'm really hoping for a great week this week. Thank you all for coming. And now I would like to call Martin to say a few words for us before we get started with science. And
thanks, Barbara. So this is slightly sad occasion.
This is for the camera.
We thought about how we were going to remember Enrique. Okay, I'll use the other microphone.
No, you have to use both.
Oh, okay. We felt rather than leave it towards the end, it would be better to do something at the beginning. And of course, I don't know about the rest of you, but I was enormously sad. It was one of the saddest days of my life when I actually heard the news when he passed away. I can't imagine how much worse it was for his colleagues in Barcelona who've worked with him for more than 30 years to suddenly lose somebody at the peak of his powers. And we have lost colleagues before, and it's always very sad. But I think the particular timing of this makes it even more unfortunate. I'm not going to talk in a great deal of detail about Enrique's career. There is a wonderful, if you can use that word, obituary published on the AAS website that was written by Jordi and his colleagues and Margarita et al. And I think I'll leave you to read that. But what I wanted to do was remember Enrique's contribution to our community. When, in the last few years, whenever he got to the conference dinner, and I thought, oh, I'm going to enjoy this and I'm going to relax, I'll get a little tap on my shoulder. And Enrique would have sidled around the outside of the table and he would say to me, Martin, you must say something. And I would say, no, Enrique, you should say something. And he would say, no, Martin, you must say something. And so this became a little ritual. And I feel the metaphorical tap on my shoulder right now. And so it is a great honor to me to be able to say something about Enrique. Enrique was a wonderful scientist. It's hard to recollect just how much he contributed scientifically to our discipline. I worked with Enrique for a long time. I never published very much with him, but in particular, we were close collaborators on the Gaia space mission, which he supported hugely. And you'll hear some of the fantastic results that are coming out of Gaia right now today after the release of DR2. And Enrique would have been enormously pleased about that. And I know that he was waiting there to exploit that database. It's very sad that he can't do that. But more than a scientist, Enrique was a great human being. He was one of the friendliest people I have known in my career. And I think I've known him since my first encounter with the White Dwarf community. And his contribution to that community has been absolutely tremendous over the years. And I think the best way we can remember him is to continue that open, friendly, sometimes competitive, but always competitive in a friendly and constructive way that our community operates within. It's the friendliest group of people it's been my privilege to work with over the decades that I've been in astronomy. And I think we set a great example to the rest of the astronomical community in the way we conduct our business. Very often, when somebody's passed away, you ask for a moment's silence. I don't think that's appropriate, and I don't think Enrique would have wanted it. I think what we ought to do is commemorate Enrique's tremendous contribution to the European White Dwarf community workshops and the community worldwide across all the countries that are involved in this discipline with a long and sustained round of applause, please. Thank you. I don't think you'd have wanted more than about 30 seconds. So I'm not able to stay for the whole meeting, so I won't be around for anybody to tap me on the shoulder at the conference dinner because it's my wife's birthday that day and I need to get back. So I just want to warn you that I shall be singling somebody out during the course of the next few days and tapping you on the shoulder and say something, and I hope you're able to do that. I'd just like to move on to the next slide before I wrap up and we get on with the real business. Because Enrique worked very closely with me on this project, which was to try to get an IAU symposium on white dwarf stars. There hasn't been an IAU symposium on white dwarfs for many decades. The last IAU meeting that I know of was the IAU colloquium in Dartmouth in 1988. So I think we've been very fortunate to achieve this. And when I submitted the proposal just before Christmas, that was just after hearing the news. And the first thought in my mind was, I wish Enrique was here to see that. And when we got the announcement that we were actually successful, the first thought in my mind then was, I wish Enrique was here to get this news. So I think we celebrate Enrique by pushing ahead and doing all this wonderful science and then reporting on it. And I'd like to invite you all now to participate in IAU Symposium 357 in Hilo, Hawaii, next year, October 21st to 25th. CE Shu is hopefully here somewhere. She is the local organising committee chair for her sins. And what we're trying to do at the moment is set up pre-registration. So please sign up because that will help us judge the scale of accommodation that we need. But obviously this goes beyond the white dwarf community. So if you have contacts into other communities that are interested in white dwarfs, and this is our task, selling white dwarfs to the rest of the world at this symposium, please let us know who to contact and help us with the email list. And I'm going to hand back to Barbara. Thank you.
Is this switched on already?
This is for the stream. Keep it the closest you can to.
This is the.
This is and the green one is for the yes. So our first talk is by Stefan Jordan. It's the guy at year 2, white words, warnings, and caveats. I have here some cards.
Yes, but I'm not finishing at 9:30. So I have 2 microphones now, or what?
Yes, 2.
Oh.
So the speakers will have 2 microphones. One is for us and the other one is for the camera.
Yeah, can we switch off the light when the video starts? Actually, because it's very bright here. So nevertheless, I will start. Yes, I'm here to talk a little bit about Gaia DR2. Actually, although I'm now here for my 17th White Dwarf workshop, plus the symposium, the IAU symposium, I'm not working anymore very much on White Dwarfs. I'm sharing one poster and a talk where I'm involved in, but otherwise I will talk on Gaia DR2 because this is what I'm working on for a long time. Gaia DR1, actually published in September 2016, was a big disappointment for all White Dwarf people because we only saw 6 White Dwarfs, single White Dwarfs in it, but and some main sequence stars where the White Dwarf is the companion. But now we see, and I hope is possible, 260,000 White Dwarfs in the Gaia DR2. This is coming from the catalog by Nicola Fossile Gentile, where I'm involved in that catalog a little bit by giving some advice. And so you see it really has changed the field, and I saw so many talks where Gaia is already mentioned in the abstract, so that I see that this will have a great influence. So why does it not proceed with a... I cannot switch here. Yeah, can you go forward just because it doesn't work here? No, it doesn't work. It's switched on. Probably it's not inserted in the. Okay. So already from the Gaia collaboration, that is not really, this is only science demonstration. One thing came to the first time in view, and that is the splitting of the cooling sequence of the White Dwarfs into 2 sequences. And the interpretation of that, I will not go into it at all, because that is also already in the literature now seen from different viewpoints. But I think this really demonstrates the fantastic precision of the Gaia data and its influence. And still, next one. Next slide, please. These are all the fields which Gaia contributes to, and one of them is White Dwarfs, and I put it in one of the special positions. And go to the next slide, please. 177 papers have now been published based on Gaia DR2 since April 25. 12 of them are based working on White Dwarfs, and here are all the ones that I found. Maybe there are more which I didn't find. And so you really see already the big influence since only a few weeks now. Next one. Oh, so here's something missing at the. So there are 3 catalog papers, so to say. One catalog of the Gaia White Dwarfs within 12 parsec, one which is more on the ones within 200 parsec, and one which tried, the one that I was mentioning, trying to get the most probable White Dwarfs that are in the catalog, and to try to get around all the filtering that is necessary in such a catalog. And I will show a short video of that in a moment, so just to have some fun at the beginning. Next slide, please. This is the video, and here we are in Texas. And now we are leaving the Earth, and all the stars that you see are either from Hipparcos or from Gaia. And now we are going to Gaia, 1.5 million kilometers away, and see this fantastic satellite. This is made with Gaia Sky, a program which you can download for Linux, Windows, Mac, and you can really fly around through the Gaia catalog. And now we are switching not to the stars that we see with Gaia, but to the 260,000 star catalog. Now we only see the white dwarfs, and still there are many of them. And so it's different from the 6. The sun is still there. It's a pre-white dwarf. So, so now we are going outside of this region in our solar system, and we are going further away from our sun and more. And then we see the first white dwarfs going, no, these are the planets and the sun. And then in the next step, we will see the stars moving. And we are going outside. And this is the 260,000 star catalog. And isn't that something nice to see at the beginning? I mean, and now we're going with, this is the part in the Milky Way. Now we are blending over this artist's view of the Milky Way to just see where we are with this catalog. Yeah, please go to the next slide. And we have also a full sky view, where this is the normal view of the normal stars that we have, and then we blend over to the white dwarfs. Now we see only white dwarfs. There is a little bit of a problem to get all the stars in the center of our galaxy due to the absorption and so on. The bright one is Sirius B, as you see, and now they are moving according to the proper motion, and this is 1 trillion times faster than in reality that the stars would move. This is how the white dwarfs move. And if you look into that detail, but you can also go to the YouTube link and see that yourself. Okay, now something about Gaia DR2 as a small description and some warnings and caveats. I didn't want to start with these warnings, but with the nice things about white dwarfs. So next slide. See ya. Okay. Oh, now it works. Yeah. Okay, so Gaia DR2 is based on only 22 months of observations. Please take that into account. It's only a part of the 5-year nominal mission of Gaia, and the epoch is 2015.5. The publication date, you know, was April 25, because many of you already went on that day to the servers. 1.7 billion stars have only positions and G magnitudes, that's the total Gaia magnitude, but 1.3 billion stars have parallaxes and proper motions, and also what is as important as that, the BP and RP magnitudes for the photometry. Still not working again. Sorry, next please. So the 5-parameter solution, which means we have the position at a reference epoch, alpha and delta, we have the proper motion and the parallaxes. These 5-parameter solutions are much more than in the first Gaia catalog, where we had 2 million stars, but only 6 white dwarfs in them. This is 12,000 times more than in Hipparcos and 700 times more than we had in Gaia DR2. And the precision is much better than in Hipparcos and DR1. It's Hipparcos precision at about the 20th magnitude and about, rather than about 10 for the Hipparcos. And if you compare the proper motion, which also is of course very important for white dwarf studies, you sometimes find differences with either Hipparcos or other catalogs like PPMXL. That can mean that you have errors on either side, also in the Gaia catalog. But it could also mean that we have measured with Gaia the motion in the 22 months. And so a long-term binary would have a binary component of that. So you might also identify some binaries by seeing a big difference between the Gaia data, or a significant difference between the Gaia data and the former catalogs. Next slide, please. Yeah, the precision compared to Gaia DR1 for the parallax is really tremendous. Here's the precision in microarc seconds. And here we have the data in DR2 and DR1, and at 15th magnitude, we reach about 30 microarc seconds. That's about 6 centimeters at lunar distance. So a change in position by 6 centimeters at lunar distance is something that Gaia can measure at 15th magnitude. And this is the nominal precision for 5 years. And you see, we reach it already at the faint end, and the best data are around 13, 14 magnitudes. And that's very nice for white dwarf work, because many white dwarfs are in that region where you have the best data. Now, some warnings. Some of them I mentioned already 2 years ago. Don't just assume that the inverse of a parallax is a distance. That's very, very dangerous one. First of all, you see that, of course, in Gaia, you have insignificant parallaxes. You have even negative parallaxes. And you have, of course, outliers and so on. And just a warning, if this is the true distance, and here you have a Gaussian distribution, the measured distance by 1 over distance is not a Gaussian. Neither the mode nor the mean is the same. Only the median is the same as in the 1 over parallax distribution. And here is a sample where we assumed a large error of 2 mass. And if you use the true distance versus the distance from the parallax, in that case, you would overestimate the distances by 14% on average and the luminosity by 40%. So be very, very careful with that. If you want to have the distance for a star, like a white dwarf, you have to use additional information. You can make a Bayesian approach like many have, like it was done in these papers, where you have a realistic distribution of the stars involved. You please go to the online documentation where you also see a paper using Gaia parallaxes as a warning. There is a small critic. It does not include the selection function of Gaia. So if you do it right, you would also have to do that in addition. Also, something that you can make wrong, CDS in Strasbourg uses always the position and the data for 2000. If you just transfer them to some different epoch, then you go back to 2000, and then you go forward to some date, for instance, 2018.5 now, and you are making, so to say, you are exaggerating the error, but if you take into account the correlation term, it's fine again. But better use the original data archives and use the epoch of 2015.5 to proceed for the The systematic errors are of the order of 40 microarc seconds, so of the same order of magnitude than the best statistical errors. They can also have color terms, dependencies on the PSF, basic angle oscillation, some problems with Gaia, and averaging over many is certainly not easily possible. Please take into account the systematic errors, either add them the systematics quadratically to the averaging of the random errors. Better separate both, or it's still better if you have any thing where you know what should happen there, please include that. Also take into account there is a parallax 0 point shift in the Gaia data. For the quasars, this is the distribution of the parallaxes of the quasars, which should be 0, and it shifted to 229 microarc seconds, so you have to add that to the catalog value. However, for other objects that can be different, and of course for white dwarfs it may be very similar, so please at least take that into account. And also there are systematics spatially resolved. This is the LMC, where you see here the median parallax, and you see that on a 1 degree level, there is a change in the order of 40 microarc seconds from one position in the sky to the other. There are also large-scale systematics of 20 degrees and others. Please take into account not only the errors, but the correlations of the parameters, the astrometric excess noise, the photometric excess factor, some other data which are in the Gaia catalog. Don't just take them for granted without that. And if you investigate specific white dwarfs and you do not look them up in Gaia DR2, your paper is definitely missing some important information. Gaia is a teamwork of more than 450 people, mostly in Europe, and I just wanted to mention that this is something which you should acknowledge if you write a paper. And since I have given my talk, another 700,000 stars went through the focal plane of Gaia. 7 million astrometric measurements were taken, 1.4 million during this talk of photometric measurements. And in Gaia DR2, at the end of 2020, we will have better systematics, more stars, binaries, and the BP-RP spectra. And we hope we already have we will get the approval for another 1.5 years in November, and that will dramatically increase especially the precision for the proper motion, because that goes with t to the 1.5 rather than t.0.5. And now I'm at the end. Thanks. Yeah.
Yeah. So our next speaker, and everything. So.
Just because it didn't look here.
Our next speaker is, and then we invite after Marcus talk, we invite like Stefan.
I feel
so Martin will talk about the fundamental properties of white dwarfs with Gaia DR2.
I think the thing is on the way to the computer for the click.
It's working now. I figure we'll just.
Okay.
I'm waiting for the person who knows what she's doing to do it. So it's fantastic to be able to talk about Gaia. It's been the best part of 20 years of my life working in the Gaia Deepak, along with Stefan on a slightly different part of the project, doing the sort of photometric work. And I'm going to try to be fairly brief because I know we're short of time. I'm going to talk about the white dwarf mass radius relation as something that might come out of all this data, how we might measure it in principle. I thought it was worthwhile mentioning Hipparcos because we seem to forget that there was a precursor to Gaia, and then I'm going to talk about the work that I've been involved in on the Gaia DR2HR diagram and the white dwarf stuff that comes out of that. So I don't think I need to convince anybody in this audience, because this is a slide from a talk I gave to a bunch of people who know absolutely nothing of white dwarfs, how important it is that we measure the mass radius relation. It helps us determine the ages of clusters and the galactic disk, limits on the age of the universe, underpins our understanding of production of stars at the end stages of stellar evolution, understanding matter under extreme conditions, and I see Ross sitting on the end there, so he knows a lot about that, and about type 1a supernova progenitors. So let's move on. But actually measuring the mass and radius has been a huge challenge. There are a number of ways you could do it. These are a bunch of equations that relate measurable parameters to mass and radius, but none of them give you a completely independent answer. However, if you have the parallax, which we now do, then that transforms these measurements completely, because you have a starting point which we haven't had in the past at all. We did try to do it with Hipparcos. Unfortunately, Hipparcos was far less sensitive than Gaia, although it was a great mission in its own right. And Judy pulled together 20 years ago now, I see, which makes me feel quite old. And I hope it doesn't make Judy feel old as well. Of the measurements of the mass radius relation for white dwarfs in the Hipparcos catalogue. You can see there aren't many stars, a bit more than a dozen, and the error bars are fairly uncertain, so it's very difficult to draw any substantive conclusions from the Hipparcos data, because white dwarfs are at the very faint end of what Hipparcos could observe, and the observations were extremely challenging, and actually often the output was wrong when you look at in detail at some of the objects. Nevertheless, it got us moving in the right direction and certainly stimulated those of us who work within the European Space Agency to think about what came after. and really was the birth of the Gaia mission. So this is the Gaia DR2 HR diagram, the full DR2 color magnitude diagram from a selection of filters, which are, the details are published in Babuzio et al. 2018, which comprises 65 million, well, nearly 60, let's call it 66 million stars with it among friends. It's almost 66 million. And within that are around about 200,000 white dwarfs. I've put that in inverted commas because, yeah, there are a lot of white dwarfs, but actually it's not necessarily straightforward to identify quite which are the white dwarfs and which might be artifacts or problems in the Gaia data. And Stefan gave a very good description of some of the limitations that you need to take into account when you're working with Gaia. For the work we did on the diagram paper, we imposed a stronger parallax constraint, which reduces the 200,000 to about 26,000, but produces much more reliable set of identifications. This slide is an illustration from a practical point of view of what I mean by how careful you need to be. So this is just plotting the parallax, or rather 1,000 over the parallax, effectively the distance, against the error on that. And you can see this sharp edge here is created by the cutoffs we've already applied. And you can see there's a bit of a bipolar distribution. So here, where we have low parallax error, are pretty certain to be white dwarfs. These look like white dwarfs in terms of the absolute magnitudes that you get, but I'm sure many of them aren't. You can see at the very sort of low distance end, since Sirius B at 2.36 parsecs up here is the nearest white dwarf that we know about, it's very difficult to believe that there are any others that we haven't already found that are nearer than that. So I think that just illustrates the care that we need to take in dealing with the catalogue and don't overinterpret. Just as an aside, one of the things that comes out of the diagram paper are cluster diagrams. And I spent quite a lot of my work with colleagues over the last decades or so trying to identify white dwarfs in clusters, because clusters have a known age, and therefore white dwarfs are important diagnostics on the ages and understanding of the stellar evolution processes. Of course, if you look at Persepi and you do your HR diagram, you have the absolute magnitude of every object in it, and so you just pull out the white dwarfs trivially. So all the pain that we've gone through over many decades to try and find all the white dwarfs evaporates overnight with the creation of the DR2 catalogue. And here are the Hyades white dwarfs. Most of these we already know, but after a lot of hard graft. And just this is now the cleaned up HR diagram, removing some of the extraneous noise. You can see the white dwarf distribution. You can see the pre-white dwarf stars that are highlighted over here. And when you start to analyze this more carefully, so the blue smooth curve is a fiducial that sits, in this case, on the main evolutionary tracks, and in this case, on the white dwarf evolutionary tracks. And the green ones illustrate the scope for detection of binaries, because, of course, we don't necessarily know that all the stars are isolated, and unresolved binaries will create a distribution of absolute magnitudes that we need to somehow get to grips with. Stefan already showed this slide, but I'm not going to apologize for showing it again because I actually produced this one. So this is the white dwarf cooling sequence. You can see a strong hydrogen-rich cooling sequence here, and the split, which I think probably is a subject of a bit of debate, which I'll discuss a little more in a moment. And then there's all kinds of features, this sort of broad feature here, which I have no idea what the explanation for that is right now. So constraining and cleaning up the sample a little more, this is now the white dwarf cooling sequence plotting the evolutionary curves from Pierre Bergeron, and I'd like to thank Pierre in public for working with me and putting these through the Gaia bandpasses, without which I could not have done any of this work. So the purple curve, and the purple curve in all the subsequent plots is 0.6 solar mass hydrogen track. The blue curve is a 0.6 solar mass helium track, and the dashed green one is a 0.8 mass pure hydrogen track. So you can see the scale of how things behave on this plot. And obviously the hydrogen-rich sequence is pretty nicely reproduced, but there isn't much of a helium sequence, and this sequence appears to be over here. So is that helium or is it not? I'm not sure at the moment. I think it probably is helium, because when you look at the color diagram, these stars that sit over here sit on top of the helium sequence perfectly in the color diagram. So I think what's going on is that we've got some residual uncertainty in the band passes, and therefore when you fold these through the Gaia band passes, you're getting a little bit of systematic error in there. So work needs to be done on that. And you see the same, this is the sample of stars from the SDSS catalogue that appear in Gaia. Colours are the same. This is the colour magnitude diagram of the SDSS stars. Because the narrower bands, you get a better split between the helium and the hydrogen curves. And here you do reproduce the helium curve quite nicely. But it's interesting to see that the hydrogen curve, the purple one, is not right down the middle. And I think this is a further indication of the uncertainty I was just talking about. So taking the 26,000 stars and looking at the volume density, I think is an interesting exercise. Firstly, you can get an idea of whether or not the volume density we're seeing matches previous work, and it's not far away. I'm not going to talk about that in detail because there's really quite a lot more work to do to thoroughly understand that. But I think it's worth showing this cumulative plot. So what this plot is showing is the volume density calculated from all the stars within the volume at the distance on the plot. So this point here is all the stars within 20 parsecs. And here, all the stars within 40 parsecs. And it gives you a good feel for what the completeness is, because although there's a lot of scatter where the numbers are small, it converges on something roughly flat up to about 40, maybe 50 parsecs, and then it starts to roll off. So clearly with this 26,000 star sample, we're not complete beyond 40 or 50 parsecs, but it looks pretty good below that. So conclusions. The work has been confined to many fewer stars before the Gaia DR2 catalogue was available. It could be more precise for binaries. We did quite a lot of work with binaries from the Hipparcos era, because the parallaxes of the primary stars were actually very accurate, and therefore the distance we could apply to their companions was very well known, but that was a very small number of objects. DR2 is already being transformational. Stefan listed the number of papers in little more than 3 months, and it's going to go on and on and on. And I see DR2 not just in our own subject, but actually in astrophysics as a little bit of a tidal wave that starts very slowly and will eventually roll through the entirety of our understanding of stars and galaxies over the next few years. I've talked about the white dwarf specifically in DR2, and there are going to be more talks to come. So I'm not going to steal any of their thunder, because I've had a bit of a preview of those, and they are going to be good, believe me. We do need to be careful about the remaining limitations on DR2. Stefan talked about parallax limitations. I think the band passes need further work, and I also spotted a paper, I don't know if you picked this one up, Stefan, by Weiler, which is an archive now, but he hasn't yet published his reassessment of the band passes. It'd be interesting to see what they are. So I got a minute left, so I'm a good boy. And I think the best thing I can do is just finish off with the Gaia DR2 sky.
So we have Stefan, can you please? Stefan. Oh, sorry. So Stefan, you can come up. We have 5 minutes for questions for both speakers.
So we need to get close together and share the mic.
Of course.
Hello, guys, from Marsh. Question for Martin. Why do you suspect band passes rather than problems with model atmospheres? Because between the DA and DB, it seems to affect DB more than helium atmospheres.
I think because the problems are not constant in those two sets of atmospheres, and I think we can say the atmospheres are pretty well understood in those temperature ranges. I'm not saying that it's they're the ultimate, at the ultimate level. I'm sure we'll find some things, perhaps from the work that people are doing around the line broadening experimentally. But I think I would expect a consistent difference, and it varies so much between the colour and the absolute magnitude HR diagram.
Well, it will be kind of one of the conclusion of my talk after break, but my conclusion is that there's absolutely no problem with the models and everything is fine. We'll see later.
I believe you.
Well, one of our conclusions is that there's no problem with the Gaia methods. So,
Okay. That's an interesting perspective. Particularly because there was because of that paper published. So
You'll get all the answers in my talk.
So there's got to be a problem somewhere.
I was just going to say, it doesn't apply to white dwarfs specifically, but in dark energy surveys, we're finding most of our uncertainties are the bandpass uncertainties.
Thank you, Bert. So DR3 is it still scheduled to come out in late 2020? And give a sense of how, it's obviously a longer baseline, but how much of an improvement that will be for what?
It's still the official date, which means that it could be shifted. But I'm not saying anything about that. I'm not allowed to say anything about that. But I'm sure it will be our goal to be very close to this date. And it's hard to say how much we will improve, especially on the systematics. I mean, we are about an order of magnitude and more away from what we wanted to have for the final Gaia catalog, as far as the systematics are concerned. And this is a very, very tough business. We are already working on Gaia DR3 since about half a year now. And so it's while the DR2 wasn't published, it's already began, and it will become more and more difficult to get better. But I'm sure we will be much better. But additionally to that, we will have the BPRP spectra, where you can see the structures in the energy distribution of the stars, and that will certainly help against the simple integration over the BP and RP filter in that case.
Any more questions? Let's thank both our speakers. And our next speaker is Mark Collins, and he's going to be talking about revisiting the white dwarf local sample in the era of Gaia.
Okay, is this close enough? Okay, you can hear me. Can you full screen? Okay, great. Okay, so good morning, everyone. I'm Mark. I'm a postdoc at the University of Warwick, and this morning I'm going to be talking to you about our recent work revisiting the 20 parsec local sample, making use of all the lovely new Gaia data. You may have already seen this work on arXiv about 6 weeks ago, or the accepted version is on arXiv today, so please check that out if that interests you. So the structure of the talk is going to be fairly simple. I'm only briefly going to talk about the identification of our white dwarf sample, but what I really want to talk about is just these two aspects here, which were just two parts of the project that I found particularly interesting, and the reason being that with these near universal Gaia parallaxes, you can almost take a different approach to how you tackle these two parts. So first of all, identifying the sample, we need an HR diagram, of course, but not this one. This is our HR diagram. And so all the points here are all the objects within Gaia with parallaxes that would place them within 20 parsecs. And of course, we have a main sequence and a white dwarf sequence. But what we first noticed really was that there's a lot of scatter points here and down here. And These we found corresponded to sources near the galactic plane with very high astrometric excess noise. And so we placed a quality cut of 1 milliarc seconds, which are these points circled in red. And then from there, we were able to cross-match the remaining points with the known 20 parsec members, which are highlighted in green. So there's 130 of those. And we could then make a nice cut in the HR diagram in here. And we were left with 15 sources left to check against to see if they were potentially new white dwarfs. And so what we did from there was cross-match those 15 things with pan-stars and 2-mass photometry. And then along with the parallaxes, we could fit them with white dwarf models to see if they really were white dwarfs. And in 9 of those 15 cases, it looks pretty good. So we think they're new white dwarfs. But the remaining 6 cases look like things that may have been scattered into that bottom region of the HR diagram instead. So in total, 139 Gaia white dwarfs within 20 parsecs. So like I say, you can see that on Archive now, get all those TF log Gs and do whatever you want with those. So moving on. So wide binaries. Wide binaries, in the pre-Gaia sense, the easiest way to try and identify something like this was you say you've got a white dwarf here you found, and it has a large proper motion. So you look nearby and see if anything else has a similarly large proper motion in the same direction, and maybe you find that. And certainly you can take this approach with Gaia DR2, and you might do very well, but we're not using all of the information that we can, so that's what we tried to do. So the way I started thinking of this is I found a white dwarf in Gaia, and then I drew a cylindrical volume around it, and because Gaia is great and we can try and do the best we can, I went for a very large volume, so we might as well do the best we can. So a radius of 1 parsec, and in the radial direction, 1 parsec either side as well. And you probably only find a couple of stars that sit in the same volume. So I've drawn 4 on here. And then if you look in the projected image on the sky, like I say, a very wide circle on the sky, but only a few sources remaining once you've done a distance cut. So we can then put the proper motions on here. But we're not working in a physical dimension with proper motions, so we can use the parallaxes to turn them into tangential velocities, and then we can compare the white dwarf velocity with another star's velocity. And the distance between those two arrow tips we can call delta V tan, which is essentially a measure of how likely those two stars are to be bound to each other. And then we can repeat that for all of the stars within our little cylinder and stick them on a diagram of delta V tan versus the projected separation. And what you'll find is, hey, look, there's one guy down here with low delta V tan and a fairly small separation. So we found a white binary. And so what we did for our sample of white dwarfs was repeat this process for everything and stick them on a single diagram. And that diagram looks like this. So you have a bunch of objects up here in blue, which are just stars that are nearby to our white dwarfs, but they're not going in the same way. They're not bound to our white dwarfs. But you can see this diagram very cleanly separates those stars with the known binary systems, which are mostly down here. And you can see as well in that green point that we have found 1 new white dwarf main sequence binary from one of our 9 new white dwarfs. And we're not the only people to take this kind of approach. Maybe you saw an archive last week, Al Badri et al. They took a very similar approach to white binaries, but actually looking in within 200 parsecs of the sun. And so they were able to find thousands of binary stars. This is not to say that this approach is absolutely perfect and will find every binary. So in this case, you can see one of the known systems is very high up here. And the companion to this white dwarf has very high astrometric excess noise because it is actually itself an unresolved binary. And so the PPM-XL proper motion would place it down here. So practically what Stefan was talking about in his talk earlier. And for this object, the companion parallax is similarly affected, so we post hoc added it to the plot. So that's all I'm going to say about this wide binary sample, because Sylvia Toonen will be talking about this more tomorrow. And so for the final part of the talk, I just want to talk about, maybe can we move forward one? Here we are. Space density. So in principle, space density sounds like something fairly simple to calculate. You take the number of stars that you found, you divide by the volume, and the uncertainty is just going to be the Poisson error on that. So this would be very simple, but of course you might have missed some white dwarfs, and so you need to try and account for that systematic uncertainty in some way. So classically what you would do is perhaps draw the cumulative distribution with its uncertainty as a function of distance, and then over the region that looks fairly linear, you could fit a straight line through that. So previously, out to 13 parsecs, we thought we were very complete because this used to flatten out, but now it goes fairly linear up to 20 parsecs. However, from a statistical standpoint, this isn't actually a very safe thing to do because every step in a cumulative distribution is strongly correlated with every other step. It contains all of the information from the steps before it. So if you fit like this, you will be fitting the same data repeatedly, and you end up actually with an uncertainty that's far too small. So we tried to use all the information we had to try and do something that was accurate in both this value and the uncertainty. So I started by considering the two categories of object that we have. Those that we knew about before DR2 and those that were found in DR2. Of course, we have a very large overlap between these two categories, but to calculate n white dwarf, we actually need to consider a fourth number, which I've called here question mark, that sits outside the Venn diagram. And what I'll show you now is that the value of question mark can statistically be constrained by the other information that we have. So from here, I considered all of the white dwarfs that we knew before DR2, within 20 parsecs, that had parallaxes already of some description, and then looked at whether or not Gaia found them again as a function of their distance. So we have the redetections up here on the top, and the non-detections down here on the bottom. And you'll see that those non-detections that we have are generally actually closer to us than further away. And so you might imagine that there is some curve, a probability curve, that tells you as a function of distance how likely you are to find a white dwarf, any given white dwarf. And so this can actually be fitted using a process called logistic regression, where there is a standard curve called the logistic function, and its argument here, u, can be parameterized with what we call theta. And so theta can be optimized by maximizing the likelihood of obtaining this particular set of data, and we find that the curve looks like this. And you can see that actually at 20 parsecs, Gaia basically finds every single white dwarf, but within, say, 5 parsecs, it doesn't perhaps find every white dwarf for a variety of different reasons. And so what we can do is take this curve, integrate it over the whole 20 parsec volume, and what we essentially get is the detection efficiency for Gaia finding white dwarfs within 20 parsecs, and that's about 96%. And so now we now have two numbers, the number of sources that Gaia, or white dwarfs that Gaia found, and the detection efficiency from which they were found with. This has some uncertainty itself because there's a couple of objects near the 20 parsec boundary, but I do consider that uncertainty as well. But we can then use the negative binomial distribution to actually get the statistical distribution of how many white dwarfs Gaia would have missed given these numbers. And so when we calculate that distribution, it looks like this. It peaks around 5 and then drops off rapidly after that. But we already know that Gaia missed 8 of those nearby white dwarfs. So we can essentially use those as a prior to say these histogram bins are effectively untrue, and it's only these later bins that are meaningful. And so when we renormalize that distribution, we now have the distribution for question mark that you saw in that Venn diagram before. The most likely value is 0, as you can see. So perhaps we won't actually find any more 20 parsec white dwarfs in future Gaia data releases, but the median value is 2. So maybe we will find a few more in the future. And so taking all of those numbers in the Venn diagram you saw, including their statistical distributions, we find that the total number of white dwarfs has this distribution, and then convolving each point in this distribution with the corresponding Poisson process, we have the distribution for rho v, which looks essentially Gaussian now. And so rho v is just 150, give or take 13. And then, of course, we divide by the volume to get the final space density. But this includes the sort of statistical uncertainty of how many white dwarfs Gaia may not yet have even found. So we've tried to consider that into our calculation. And so I'll stop there and leave up my summary. So thank you.
So we move to our next speaker. Jay is not going to come. So we're going to move on to Nicola. Fusivo, sorry. Fusivo, sorry. White lives in the garden, too. And then we go to that part. Questions?
I'll sit over here. Okay. Hi, everyone. I'm Nicola Gentile Fusillo from the University of Warwick, and I'm going to talk about the work we've done in constructing a catalog of white dwarfs based on Gaia Data Release 2. So the first step, in order to identify Gaia white dwarfs among the 1.6 billion objects observed by Gaia, is to actually understand the space that these objects span in the HR diagram. So our first step was to take a few known white dwarfs from the Sloan Digital Sky Survey, cross-match them with Gaia Data Release 2, and produce this sort of HR diagram, which you can see doesn't look like any HR diagram you've seen. And that's because we applied almost no quality filtering at this stage, and therefore there is a huge amount of scatter. Using this sort of diagram, we define the cuts I'm showing here in red, which at this stage are very generous. They still include 8 million objects, and they're only meant to identify the area within which we intend to carry out further selection. And this further selection is a quality filtering based on some Gaia quality flag. These are parallax over error, which is self-explanatory, photometric BPRP excess factor, which can be used to spot when things have gone wrong in the Gaia color, astrometric sigma 5D max. This again can be used to spot when things have gone wrong in the 5-parameter solution of Gaia, and astrometric excess noise, which in a way can be seen as a measurement of the reliability of the parallax measurement. By applying some carefully constructed quality filters based on these parameters, we boiled down our sample size to 800,000 objects, which are the ones I'm showing here in black and red. And this is when we spotted that something else was kind of wrong with Gaia, because all of the objects in red in this area are actually in the Magellanic Clouds. And some other red objects over here are highly scattered objects from the galactic plane. So we realized that pretty much Gaia was really struggling in crowded areas of the sky. Therefore, we defined a new parameter, which we call density. And broadly speaking, this is just the number of objects in the same square degree as our object of interest. And we use this density parameter in order to apply stricter quality selection in objects in crowded area. And this allows us to completely remove contamination from background Magellanic Clouds and deal with some of the more problematic areas of the galactic plane. This second set of filtering brings our sample size down to 439,658 objects, and that is the final size of our catalog. We then immediately proceeded to cross-match these objects with all available spectroscopy from Sloan. We then inspected and classified these spectra. We find 20,759 white dwarfs and just under 2,500 non-white dwarf objects, contaminants. These are the objects I'm showing here in blue and red. And immediately you can see one thing, and that there is no perfect separation between the two objects. There is no magical cut I can create that will allow me to select all white dwarfs and reject all contaminants. So we decided to go for a different approach, one analogous to the one we've used in our previous work in Sloan, selecting white dwarf candidates. And that is to actually use the distribution of known white dwarfs and known contaminants to construct a probability map, and so calculate probabilities of being white dwarfs for all objects in our Gaia sample. The result of this is the HR diagram I'm showing here. These are all 439,000 objects, and the color actually indicates their probability of being a white dwarf. And as you can see, you get this smooth color transition. At this stage, I want to issue a warning, because cross-matching with Sloan was clearly a vital part of our selection work. And some of you may be aware that there exists an official Sloan to Gaia Data Release 2 cross-match. Is given in these two tables, but we find thousands of Sloan objects which have a reliable Gaia cross-match and are simply not included in these tables. So if you're using these tables for your work, you have now been warned. Using these probabilities, we can, in flexible ways, select subset of white dwarf candidates from our catalog, and generally speaking, you can actually select 260,000 high-confidence white dwarf candidates. And there is an 8-time increment compared to the number of white dwarfs that were known before Gaia. And to better visualize these, I made these plots over here, which are sky densities of white dwarfs, the 33,000 which were known before Gaia, and the ones that are known as of today, if you're using my catalog, of course. And something else that became quite evident when moving between a few thousand objects to hundreds of thousands of objects is that we needed to do something about naming. Because white dwarfs naming has been confusing for years. There's white dwarfs with more than 10 names. There's names that are slightly overlapping. So we decided to create a naming convention that is purely based on Gaia, and we gave this naming format, WDJ, followed by the coordinates of the objects, to all objects in our catalog. Now, these coordinates are actually given at epoch 2000, and that's because Gaia coordinates are actually given at epoch 2015.5, but this will change in future data releases. So we decided to have a uniform one.
It will be in the middle of the Gaia mission. It will always stay in the middle of the Gaia mission.
And then probably we need to change this.
Okay.
Anyway, to calculate this, we simply use the proper motions and rewind them. Some of you, because it's early in the conference and we're all paying a great amount of attention, will have seen that there is a lot of structure in the distribution of white dwarfs I've selected from my catalog. That's actually a consequence of the limiting magnitude of Gaia, and of course in my catalog, and the fact that the sky density itself, therefore, depend on the Gaia scanning law. Here, I made a sky map of the limiting magnitude of my catalog, and this structure which you see are actually the Gaia scans. So only about 3/4 of the sky go down to a limiting magnitude of at least 20, and the number of white dwarfs per square degree brighter than this limit is, on average, 4.5. But this also means that in future data releases, as this map gets more homogeneous, we're going to be able to identify more fainter white dwarfs. We also perform a comparison of our new catalog of white dwarfs from Gaia with white dwarfs and white dwarfs candidates from Sloan, and we're able to estimate that our catalog is complete between 56 and 81% for white dwarfs that are brighter than 20th magnitude, hotter than 7,000 Kelvin at high galactic latitudes. We also look at this completeness, a function of sky position, and as you can see, it's very uniform. And in fact, our completeness drops significantly towards the galactic plane, and that is because of the stricter quality selection which we need to apply in crowded areas of the sky. The histograms over here are simply to show that our white dwarf selection doesn't have any strong bias in color or magnitude, and actually the drop-off which you see here is due to Sloan reaching its saturation limit. As an added product in our catalog, we also provide stellar parameter for a subset of our high confidence white dwarf candidates, and these stellar parameters are purely calculated only from the Gaia data. But this is actually going to be explained in details by Pierre-Emmanuel Tremblay this afternoon. Some of you at this stage may be wondering, okay, what about objects that are not just single white dwarfs? What about objects related to white dwarfs, these white dwarf-ish objects like subdwarfs, cataclysmic variables, extremely low mass white dwarfs, main sequence stars? Well, our catalog cannot be complete for these objects, and neither can be fully exclusive. Here I'm showing a cleaned HR diagram, and as you can see, some objects like subdwarfs will be some of them in our catalog, but because they cluster so closely together over here, they will actually have low probabilities of being white dwarfs. But objects like cataclysmic variables in green and main sequence star, white dwarfs main sequence stars in red actually have so much scatter that they are physically impossible to distinguish purely using Gaia data. Therefore, some of these objects are fully outside of our catalog, and some of them will be in the catalog even with the high probabilities of being white dwarfs. One of the great advantages of having performed our reliable cross-match between our catalog and the Sloan spectroscopic sample is that now we have a bunch of spectroscopic objects to actually explore the distribution of the white dwarfs we have selected. In gray, in these HR diagrams, I'm showing the 100 parsec sample of white dwarfs as selected from our catalog, and the different color points are different spectroscopic type of white dwarfs as identified thanks to Sloan. It's been mentioned before that there is a lot of structure in this distribution. The extremely clear 0.6 solar mass distribution of hydrogen atmosphere white dwarfs, and the already mentioned track underneath it. And though there are some DA white dwarfs which are in blue over here in that position, as you can see over here, from this very narrow clustering on that track of the helium atmosphere white dwarfs, dB, dCs, and dZs, from this we can actually conclude that this second track is most likely the distribution of the canonical mass helium atmosphere white dwarfs. Perhaps even more interesting is this other track over here, which is transversal, so not parallel to the other white dwarfs tracks, and therefore not a constant mass, and therefore quite hard to explain with a simple astrophysical explanation, as it was mentioned before. On the right over here, I have some more exotic type of white dwarfs. In blue, I'm showing magnetic white dwarfs, and as you can see, there is quite a lot of scatter among them, but on average, they all sit well below the 0.6 solar masses track, showing that indeed magnetic white dwarfs appear to be underluminous and therefore most likely more massive than their non-magnetic counterparts. On the right over here, I have DQ white dwarfs separated in orange. I have the normal DQs, and in purple, the hot DQs. As you can see, the two families are extremely well separated, and the hot DQs actually occupy the same position as magnetic white dwarfs. Unsurprising, since we know that most hot DQs, if not all hot DQs, are likely to be magnetic. In red, I'm also showing some ultra-cool white dwarfs, which turn around and become blue again as they cool, and end up occupying their own little area of the HR diagram. With this extremely quick overview of what we've done with the Sloan spectroscopic sample, I hope I emphasize that despite the fact that Gaia is fantastic and it lets us observe, find a lot of white dwarfs and characterize them in ways which were impossible before, ultimately, we're still going to need spectroscopy in order to answer some of the key questions. Fortunately, the way we perform spectroscopy on a large area is about to change entirely, thanks to the multi-object spectrographs, which are going to come online starting from next year. And that's why I invite you all to go and see Christopher Mansell's poster, which is all about the power of these new facilities. And with this, I want to conclude. But please, I invite you all to take a picture of the screen, save these links, go and grab my catalog, please. Thank you very much. I return these.
So,
is there a clock?
Is there a clock in there somewhere? Elizabeth Jeffrey, and she's going to be talking about Gaia, white dwarfs, and the age of the galaxy.
Okay. Okay.
And then we'll go back to questions.
Okay, can you hear me okay? So make sure that works. Okay, thanks for Barbara and the organizing committee for this great conference so far. So I'm also going to be talking about Gaia and some of the stuff that our group is doing. So this is in collaboration with Ted Von Hippel, who is not here, and some of our other collaborators. So I'll be talking a little bit about Gaia and what we're doing as far as white dwarf ages go. So I think we've heard a lot about Gaia and white dwarfs, so I won't go over that too much, but then I'll talk about some of the work that we're doing on measuring ages of single white dwarfs, and then talk about some of our goals and status, and then I'm going to talk about some work that I've been doing with the Hyades as a test case to try and work out some systematic effects that we'll see and just start going towards getting absolute ages for these single white dwarfs. So we've seen this plot a few times. It's pretty awesome, as we all know. That's from the Gaia collaboration paper for HR diagrams. All of these white dwarfs in this catalog, which is really, really exciting. So what we're doing is we're measuring the ages of individual white dwarfs. And to do this, we use a Bayesian algorithm that we've been developing over the last few years. Ted's talked about it several times at previous white dwarf conferences. So we call it BASE9. So BASE9 stands for Bayesian Analysis of Stellar Evolution with 9 parameters. There are a few papers that our group has published with it. It is available. It's open source. It's available online. GitHub, if you are interested in using it for any of your research purposes, you can let me know and I can tell you how to get it installed, or at least where to go to find out how to install it. Anyway, but basically what base9 does is it takes some stellar parameters, age, metallicity, helium, distance, so on and so forth, uses a computer-based stellar evolution model, and I'll include in there white dwarf models. So you put all your model ingredients in, whether it's main sequence evolutionary times, white dwarf cooling, white dwarf atmospheres, initial final mass relation, and then base9 predicts magnitudes. It compares it to the observed magnitudes, and samples the posterior distribution of various quantities that you're interested in. So to get the age of a single white dwarf, it's relatively simple. You've probably seen this equation before, right? You have the white dwarf age, the white dwarf cooling age, plus the precursor age is equal to the total age, right? So we know to get the white dwarf age, you have to have the temperature of the white dwarf, which we can get from the photometry. You need the mass of the white dwarf, which we can get from the distance, and there's a few steps that I skipped there, but it relies on the mass radius relation, which was talked about already today. But once you get the white dwarf age, if you assume an initial final mass relation, you have your main sequence models, you can get the precursor age, that gives you your total age. Of course, for the cooler white dwarfs, the precursor age starts to matter less and less and less, and so you're become dominated by your white dwarf age. So for the cooler white dwarfs, you'll have higher age precision because you depend less on the precursor age, which depends on the initial final mass relation and your main sequence models. So how Gaia helps with this, we've talked, this has been talked about already today. We'll hear more about it later, but we're going to have these precise parallaxes, or we do have these precise parallaxes for thousands and thousands of white dwarfs, which I say is, again, really exciting. So we combine that with photometry that already exists. We'll be pulling photometry from both Gaia as well as Pan-STARRS, SDSS, a variety of available catalogs, and then determine very precise white dwarf ages. So this is actually a plot from the last talk, from the talk that Ted gave at the last white dwarf conference. But it basically shows what our Bayesian algorithm can do for a single white dwarf. This is a cool white dwarf, J1648 plus 3939. It has a temperature of something like 4,800 Kelvin, so it's fairly cool. But it shows the sample. This is when you don't have a very informative distance prior, so you don't know the distance very well. And so you can see that the age, so this is age versus distance. So the age could be anywhere from 4 gigayears all the way up here. But once you get an informative distance prior, so if you know the distance very, very well, then you can start to get very, very precise ages. So this is some simulations that we ran to say if the distance was 66 parsecs, it zooms in here, you get an age precision of about 5%. If the distance is 40 parsecs, you get an age precision of 1.2%. So you can see once you have that really precise distance, you're going to get a really precise age because you basically collapse this distribution down. And so with Gaia, we're going to be able to have these very good distance priors to use for these white dwarfs. So this is another plot that just shows, is mostly illustrative, to show how for this another particular white dwarf, if you don't know the distance very well, this distribution looks like it's pretty thin, but it's not when you look at this axis, right? All the way from 4 to 12. This is the age distribution versus number of samples. So, you get a 30% precision if you don't know the distance very well. But if you do know the distance very well, you can beat that down to 2%, 1%, depending on the parallax, the precision on the distance from the parallax. So what our program goal is that we're going to take the white dwarfs that Gaia has found, and we're going to measure the age of every single white dwarf in Gaia using this Bayesian algorithm that I've talked about. And often our age precision will reach 1 to 5%. Depends on, of course, temperature and such. I'll say a little more about that later. But so we're going to, another big thing that we're going to do is we're going to take kinematics and separate the white dwarfs, the different populations of white dwarfs. So the disk white dwarfs versus halo white dwarfs. And then measure the age of each individual white dwarf and get age distributions for the different constituents of the galaxy. And so we think that there will be enough halo white dwarfs in this sample that we'll get an age distribution for the halo, for example, which will be pretty exciting, which will tell us something about star formation history. All of these ages, once we get it done, we will make all of these ages available to the community if you're interested in them. And the nice thing about using base 9 for this is that you can really tweak your model parameters. Like you can use different initial final mass relations, for example, see how it affects the age. You can use different main sequence timescale models. So it really lets us compare models and work out some of these systematics and model uncertainties and such. So I'm going to talk for the rest of the time about some work that I'm doing on the Hyades. We're using the Hyades really as a test case for this measuring ages of single white dwarfs to see if we're doing as well as we hope to. So I just put this picture in because it's a nice, pretty picture, right? This is the Hyades. And so the Hyades we're just using the 6 individual DA white dwarfs in the Hyades. So they've all been observed by Gaia. And so I used the Gaia parallaxes to calculate the absolute magnitudes of these and then ran them through base 9 to see what kind of ages we get. The parallaxes for the Hyades white dwarfs are very, very good. They are less than 0.5% precision, which is really exciting. So again, some of the goals I hope to do with the Hyades white dwarfs, since we have really good photometry for them, we have really good parallaxes for them, we'll be able to improve, hopefully, the absolute ages of these using this technique, search for any kind of systematic effects in temperature and mass and so on and so forth, and see if there's consistency in the ages we get among all 6 white dwarfs, because they're all a member of the same cluster, and so you should get the same age, right? And see what kind of precision that we get for them. Here's the color magnitude diagram for the Hyades white dwarfs. Again, there are 6 of them. This is the apparent magnitude, color magnitude diagram. So B versus U minus B and V minus B minus V. When I shift this to absolute magnitude space, just using the parallaxes, this is still a work in progress, and I'm glad for the talk earlier about not just using 1 over the parallax for the distance, right? So we'll definitely dig into that paper.
8.5% precision.
Okay, yeah. So anyway, so we have these 6 white dwarfs here. This is the first result. So this is a sampling plot for each of the 6 white dwarfs. Basically, you can see how, I have a histogram of these in a second, which might make a little bit more sense. But you can see where the average of the distributions are. I have 2 lines on here, this solid black line and this dotted black line. So the dotted black line is basically sort of the canonical age of the Hyades, about 625 megayears. The solid line is 794, which is a log age of 8.9. That's the age of the Hyades that was found in the Gaia collaboration paper from 2018. This is the one that has been cited before. So just to kind of give you perspective of what previous ages for the Hyades are. These are histograms here. So again, the 6 white dwarfs, these 2 have the best photometry, which I think is one of the reasons, and they're also the coolest, which is why their ages are so precise. So it shows you what the mean age is, the standard deviation on that, and the percent precision. Right. So for these ones, the percent precision is because those are the warmer white dwarfs in the cluster, and so you're really dominated by uncertainties in the initial final mass relation and your main sequence models. That tends to matter more. Whereas for these 2 here, we're getting age precisions of 2 to 3%. They're much cooler, and their photometry is better, but mostly it's because they're cooler. So the initial final mass relation and the main sequence models matter less for it. This is the CMD again. I just overplotted some white dwarf isochrones just so you can see where they sit. And really, you can see that these, here, if you look here again, these are all much older ages than sort of, again, the canonical age of the Hyades. And you can see that these white dwarfs do lie closer to that isochrone than to the other one. One quick test that I ran, there's lots of things we still want to do, but one is comparing a different initial final mass relations. So I mentioned how with base 9 you can put in different model ingredients. So for these two white dwarfs down here, LB227 and HC4, I ran base 9 with different initial final mass relations to see how that affects the age that you measure. And so this is HZ4, this column, these three on the left, and LB227 is the column on the right. So if you use the Williams initial final mass relation, the vitamin initial final mass relation, or one of the Solaris initial final mass relation, you can see how the age changes, right? So this is one of those systematic effects that we're going to explore a little bit better to see how these different initial final mass relations affect it. There's still a lot of work to do on this, especially for the Hyades. A couple other things I want to do is look at photometry precision. How does the precision in your photometry affect the age that we get? As well as consistency among filter choices. So the data that I worked with today that I showed, it was just in UBV. But how do your ages change, or do your ages change if you use, say, VRI photometry instead of UBV photometry? What if you use UBVRI photometry? So what sort of different filter combinations can you come up with, and how does that affect the age, or does it affect the age? Right, so I think that will be kind of interesting. So I'll go ahead and stop there. I think I'm out of time. So thank you.
Yeah, do we have time? We have time for questions. Yes.
I want to know which models are you using to compute the ages, and how, if you're considering different methodicities also, and also how you are assuming the uncertainty from the models, from the age of the models.
So at least for the Hyades set that I just did, the models, the cooling models are the Montgomery models as of right now. And like I said, we hope to put in other models. So I think assessing the uncertainty in the models, that was the question. I think just basically comparing different model sets to each other to see what kind of scatter that introduces in the age. Yeah. And I think did I answer all your questions? Okay, awesome.
Hey, I have a question for Elizabeth as well. I was wondering, are you worried about mergers between stars in the binary system that give rise to single white dwarfs as well? Like theoretically, you would expect, based on my models, that the 30% of single white dwarfs actually to come from a binary. That might affect your ages as well. How do you deal with it?
That's a good question. I don't know that we've thought about that yet. But you're right. That's something that should be considered. I don't know if there's not a way that you can tell.
That's the question, right? How are you going to recognize?
Yeah, how are you going to be able to tell it? Maybe if the age is not what we expect, maybe that's a flag. I don't know. We'd have to think about that a little more. That's a really good question.
I can show you some plots of like time differences that we would expect.
Yeah, that would be great. I'd be interested in seeing that. Yeah, thank you.
I had a comment and a question for Mark. Marcus, you take your method and you go deeper and deeper into the galaxy. It's slower. Your cylindrical volume will start to take in lots of stars. It will. I mean, the disk all rotates with this exact same velocity. So eventually all the velocities will match. But their proper motions will be different because they're at different distances. So I would just say a warning as you go deeper into the galaxy.
Yeah, certainly we took that into account. We were looking at 20 parsecs. We're nearby. We're not too worried about that kind of thing. Certainly, if we were going further, we would want to use a smaller box.
The question that I had was, I don't think it'll have a big impact on the space density, but did you account for unresolved binaries?
We didn't.
Gaia has actually found several binaries. There's some famous ones, but there's no astrometry for the white dwarf.
Yeah.
So next to a bright star, it's just a position.
Yeah, we didn't consider that in our calculation. We mentioned that that's something that, you could improve the calculation. I think Sylvia Tuman has an estimate for 20 parsecs, and it's only at most a couple. So it might increase that by 1%, but that's within the uncertainty of our estimates. So that's, yeah.
I know you classified the contaminants from DR14, but
Yeah.
how did you select it? Because I think you lost many of the cool white dwarfs in your contaminants.
In my contaminants, so you reckon I classified some objects as contaminants that were indeed cool white dwarfs? I don't know. I wouldn't think so. We include also ultra cool white dwarfs and cool DA white dwarfs with extremely narrow lines. So these are all objects for which Sloan spectroscopy. So we looked at them. Mostly the contaminants, in fact, are main sequence stars, some M dwarfs, and actually there are still quasars. There's quasars with extremely good parallax measurements in Gaia, as it turns out.
This is mainly a question for us, but partly also for Nicola. So
you start. Okay.
You want to measure ages for all the white dwarfs in Gaia too. So how are you
that's the goal.
all? Because if you start to do these measurements for white dwarfs that turn out to be interlocutors in white dwarf space, you're going to get some very silly answers. Potentially.
Yeah, that's a good point. So I think as of right now, what we're doing, well, right now Ted's really focused on trying to find the halo white dwarfs, and so he's using kinematics to try and find those. I guess the way that we define all, probably, I think, so first of all, we're probably going to do like a cut on the HR diagram to see what we do, what we can get, and cross-match it with Sloan and some other catalogs. Maybe look at Nicola's catalog. I think, I mean, if we have photometry for them, we can run ages on them. Maybe the ages will be crazy weird, you know, but see what comes out at the other end. But you're right. That's something we definitely need to think about is how do we make sure we don't have some of these, like you said, interlopers and things that aren't actually white dwarfs in there. But as of right now, we're planning on just turning the crank on as many things as we possibly can. And, yeah. And then did you have a question for Nicola too, or was that? Do you want to comment on that? Okay.
I have a question for Nicola. Can you say a little more on the galactic plane problem? Was there like a specific parameter that was off? And yeah.
So we dealt with the galactic plane and the Magellanic Clouds a little differently. The Magellanic Clouds was simpler because we knew we had to remove all of the objects. They were background, so we could cut on the significance of parallax there. The plane was a bit harder. I think the two parameters that really were affected more in the planes was the astrometric sigma 5D max and the photometric BPRP excess. So in my understanding, what happens in crowded area for Gaia was the background subtraction gets much more challenging, and this can be better seen in the photometric BPRP excess factor. So, and therefore the color was mostly affected. Actually, it was an effect you could Mark briefly mention, and some of the contaminants were just scattered horizontally in the HR diagram. So I look at areas of I actually don't know where the question came from. Okay. I look at areas of the galactic plane where the sky density was particularly high, and there we impose higher constraints, mostly on the BPRP excess factor.
But these are spectra. I mean,
yeah, of course, it's an integrated flux of a. But it's more of a complex thing. We also keep into mind that, for example, if the astrometric excess noise is actually still really good, and therefore it doesn't matter how much you could have scattered the object horizontally. If the white dwarf started over here, maybe it's still a white dwarf, even with a bad color, because the parallax was actually really good. So the cuts are a bit more complex than that. The full description is in the paper.
I just wanted to make a quick tease. Bart Dunlap's not here yet, he's still traveling, but I wanted to tease his poster and what he'll talk about later this week about basically the horizontal branch on the DA sequence in the color magnitude diagram.
Transverse, yeah.
It sits very close to where you might expect crystallizations. And so Bart's got some interesting thoughts about that, so bring it up.
Okay. Last question.
Hi, my question's for Nicola. I pronounced that correctly.
Yes.
Did you build a dust model? Because some of your contaminants could just be white dwarfs that have been
Extincted. Yes. No, we do not have a dust model. It's not part of the selection. As in, we do include reddening web days for the parameters, for just when we're using the Gaia data to actually calculate stellar parameters. For the selection itself, not. But the selection has this, broad smoothing effect. So yes, there could still be objects that have been so affected by dust that scattered outside or scattered in regions where white dwarfs shouldn't be. But for that, we don't account for yet.
Let's thank our speakers at the end. So now we move to the other room, to the Santa Rita for coffee break, and we meet again here at 11:15.
So, did it go? So far.
we have spectroscopy that can allow us to move them in the proper spectral type. So here's an example of one of the Gaia candidate that was observed by Carl Millis and published a few weeks ago. It's basically a twin of G74-7, the first DAZ white dwarf. So it's now in the white dwarf database. And now that we know that's a DAZ, so we have the spectral type that is included. So this CND here doesn't count anymore. So one down, 9,561 to go to complete the 100 parsec sample. And of course, if you observe a white dwarf candidate, please let the community know. So just send me an email. You say, oh, I observed this white dwarf. This is a DA or this is a DB. And then I can put it in the database, and this will go away. And then we know we don't waste time at the telescope to reobserve star that has already been observed. And if you want to share your data, you can do as well. Once your paper is published, it's up to you. We can hear Carl Millis accepted to put the paper online, and everything is there. You will notice also there is two columns here, one called MWDDH and MWDDHE. So these are pure helium and pure hydrogen solution for all the stars that are now added. So we have the temperature, log G, and masses for all the stars. What we did, we fit the pan-star grid photometry or SDSS UGRIS for all the stars in the Montreal White Dwarf database and all the Gaia candidate within 100 parsec. And you have a figure of that in the database for everyone to use. We put everything except, well, there's a very low mass star and very hot object that are out of the grid that are not there. And DQ, DZ, and DBZs are not there because there's an upcoming paper that will update those parameters very soon. So when you do all the various plots that you can do in the database, we use a pure helium solution. But as time goes on, we will be able to know what the candidates are and put the right solution. Warning, many of these solutions will be wrong because not all stars are DAs or DBs. Some are double degenerates, or some are magnetic, some are white dwarf plus M stars, or whatever. So there's a lot of parameters that will be updated as time goes on. So this is just an indication of what it could be. So if you look at the 100 parsec sample, here we fit all the stars within 100 parsec sample using pure hydrogen and using the pan-star photometry. And this is what you get. So this is like something very different than what we're used to know. Well, first, there's this little low mass density here that, well, I won't have time to talk about it, but if you have questions, you can talk to me personally. And there's a little big blob over there that I'm going to try to explain in a minute. So here's the famous color magnitude sequence. So you see the little gap here that separates, as Nicolas said, the DAs, the hydrogen-rich, and the helium-rich white dwarf. And if you put the sequence over there, you have the pure hydrogen from 0.4 to 1.2 solar mass. So you have a sequence here at 0.6 solar mass. And here, if you assume hydrogen atmosphere, you think that the second sequence here is massive DA white dwarf, so that's why you have this little blob here. But in fact, as Nicolas pointed out, they're not hydrogen atmosphere white dwarf. If you look at the helium sequence, you see that the 0.6 helium sequence goes like in between these two. And many people were quick to jump to the conclusion to say that the helium models were wrong. Not, they're correct. The reason that we see that is because these stars are not pure helium, period. And here you can see it right away. With a few clicks, you can do this diagram in the Montreal White Dwarf database. And if you look where are the DBs are here, over there, and below about 10,000 degrees, you don't have a DB. You have a DZ, a DQ, or a DC. So let's look at the DQ. The DQ are here on the lower sequence, and the DZs are also there on the lower sequence. And the reason they are there is that at low effective temperature, helium is neutral, so we have very little free electrons. So if you compare with the DQ or DZ, where you have a lower ionization potential, you add free electron, which increase helium minus free opacity. And that is why you have this little lower sequence. A white dwarf with heavy elements will mimic the color of a higher effective temperature model with pure helium atmosphere. So if you use pure helium atmosphere to try to find them, you get the wrong mass. And that's why you get a feeling that you don't have, there's something with wrong with the model, but this is not the case. So the lower sequence is simply a helium minus free sequence, if I may say. And this was known for a long time. In one of my first paper in 2005, you see that if you compare the solution from pure helium to helium plus carbon, you overestimate the mass and the temperature of the star. And you can go back to papers by Detlef Koestler in the 80s where the same effect was explained. So there's nothing new here. What about the DCs? You have a lot of DC white dwarf that are also there. And the DCs, you don't have metals, you don't have carbon in there. So why are they on the sequence below here? And if you look at the gap, well, here is a log G equal 8 sequence for a pure helium, and the DCs would be around here, and the sequence go right in the middle. So what's wrong? Well, the thing is that these stars are simply not pure helium. If you put a little bit of hydrogen, whoop, there you got the right solution. And this amount of hydrogen required to go there is about what is expected if you have thin hydrogen layer DA that convectively mixed and become helium white dwarf. So this is what you have here. This is a sequence of former DA white dwarf that changed into helium white dwarf with trace of hydrogen. So the very fact that we see a little gap in between the two sequences, that tells us that's pure helium atmosphere, something that is very rare. There's always contamination by metals or hydrogen. Here, to put the nail on that, here you have the DZA, stars with hydrogen, and you can fit the H alpha, so we know we have the right contribution of electron, and we have 0.6 solar mass. If you look at the DZ that have no H alpha, we get a higher mass. So there's an unseen trace of hydrogen. If you had this unseen trace of hydrogen, then the mass comes back to 0.6. So there is unseen hydrogen in these stars, unless you believe that the DZ and DZA are two different populations. So here are all the stars from Montreal White Dwarf database, fitted with either hydrogen or helium, depending on the spectral type on the database. So in green, the non-DA, in red, the DA. And if you put a little bit of hydrogen, poof, your mass go down. And then you get your sequence at 0.6 solar mass as expected. So here, this is the mass distribution of all the stars within 100 parsec fitted with hydrogen atmosphere. Once we we throw away all the stars that are not DAs, what will happen that these will go away, and we'll have a mass distribution that will be very similar to the mass distribution of known DAs. A quick word about the D. Yeah, about the D. Well, I will jump down. Pierre Manuel will talk about that, but here you have the sequence of massive DAs. And if you look at these stars in a mass temperature diagram, they are all here. I'm not going to say anything more about that. And the DQs, you have the hot DQs over there, and they cool down, and they turn here. And these stars, there's a poster by my student, Simon Coutu. You have the mass distribution, 0.6 mass solar. So if you use DQ models, you get the right masses. You have this high bump mass here. And if you put that in the diagram, the high mass are all there, and the normal mass are all there. And what's interesting about these one here, if you look at the velocity, well, if you have a population of stars, the older the population here is, the higher the velocity dispersion will be. And if you look at the velocity distribution of all DAs, taking from the sample from Cynthia Genet-Beaulieu that she will present tomorrow, when you look at the massive DAs, you have a lower transverse velocity dispersion, because since these stars are more massive, the progenitors were more massive, and they spent less time on the main sequence. So that's why you have this difference. And you look at the massive DZs or the massive magnetic white dwarf, they all fall on this line here. If you look at the massive DQs, you have that over there. So the velocity is much higher. The explanation for that is that these stars would actually be mergers of white dwarfs. So you just reset the clock, and you have to add the total age, the age before the merging event to that. So if you look at the DAs, there's practically no DAs with a velocity higher than 50 kilometers per second. If you look at DQs, it's more than 40%. So these stars are mergers, probably mergers. So conclusions, The number of known white dwarfs is exploding. You can help us to keep track of all that by contributing to update MWDD, send emails when you can if you find something that's missing or you know what the candidate is. Current model works just fine. You just have to use the right models. So there's no problem, never was. There's almost no such thing as a pure helium atmosphere below 10,000 degrees. There's always contamination, and massive DQs are probably result of mergers. Thank you.
So we're going to move to our next speaker, Santiago Torres, and his talk is the Gaia white dwarf population within 100 parsecs.
What do you put here? Here. Sorry. Okay, perfect. And this is for, okay. And the laser?
The laser is the green one.
Here? Okay. Hello? Okay. Okay, what I'm going to try to explain is our analysis of the 100 parsec population, obtaining also from Gaia. And basically, where I will start with talking about our population synthesis code, that is our reference to understand theoretically what is doing with the Gaia population. Then we analyze our data sample from the Gaia data release 2, how we derive the parameters, and our last studies that are concerning how are we able to identify some of the galactic components of the Gaia population. So our code is a code that has been used during 2 decades. It's a robust code, at least we think that it is, because we have been used it in different studies of the components, thin, thick, halo, bulge, and so on, globular and open clusters. In fact, the first studies about the Gaia possibilities were done by this code also. And what we have improved here is a detailed description, a detailed simulation of the different components of the galaxy, the thin, thick, and halo, for different star formation rates, scale heights, kinematic properties, and so on. Also, we introduce, here, we introduce the most updated evolutionary sequences for DAs and DB, in this case are pure DBs. Current sequences, CO, Cisneon, different metallicities that has been done by La Plata group. And also what is important in all the simulations is to include all the errors, photometric, astrometric errors, to simulate as much as possible the observed sample. So with this simulator, we obtain our first interesting result, that is the completeness of the sample against the distance, taking only these 2 criteria initially, G minor than 21, and that the parallax errors is minor than the 10%. And we observe that up to 100 parsecs, we can consider that the completeness is nearly complete. And from 100 parsecs and above this distance, dramatically drops the completeness of the sample. Okay, and so we can distinguish that up to 100 parsec, we are referring, or the samples can be considered as volume-limited samples, and from 100 parsecs and so on, need to be considered as magnitude-limited sample. So this is the reason why we select this distance, our study. The second important thing is with our simulation, we have a diagram where are the single population located. Okay, black points are the white dwarfs up to 100 parsecs, and green points are objects, white dwarfs below 100 parsecs. So we are going to study this box here, because in this region we have CO, mainly CO white dwarfs, and with a range of temperatures between 8,000 kelvins and 6,000 kelvins that we are going to see which are this important to derive the parameters. So with the help of our simulators, we can define, with our simulator, we define the region of the diagram, and then we apply a series of criteria about parallaxes, error in parallaxes, also the flux factor, and the different errors on the different band passes. And then we can select the population of Gaia white dwarfs within 100 parsecs, that are this black point here, and these gray points are contaminant that could be eliminated by these criteria. So, from this, we have obtained our catalog of 100 parsec. We obtain a white dwarf density that is slightly higher than other results, 4.9, but within the error bars. The contaminants that we have estimates is very low, and we have around 8,200 objects that are candidates to CO and oxygen neon, respectively, white dwarfs. The results has been published here in the Spanish Virtual Observatory archive that could be consulted in this web, and also we have published a paper that has been accepted with all our results. And then how we derive the parameters, this is a very important part of our study. We use what is called the BOSA Virtual Observatory tool. That mainly is a tool that could make a cross-match with different catalogs, as the Pan Star, Galaxy, and so on, Sloan, and so on, and then obtain more photometry data for the different objects. And from there, we feed the spectral modes for DAs, the mode given by Koester, within the range of 80,000 Kelvin and 6,000 Kelvins. We feed this spectrum here, and then we can obtain the effective temperature, luminosity, given the distance that is provided by Gaia. Then it's straightforward to derive the radius, the log G, and finally the mass. This has been done and for a subsample of objects, around 60% of all the objects within the 100 parsecs. This is basically the different parameters that we have derived. The gray histograms are the observed results, and the red lines are what we expect with a simulation of single stars. Basically, the most important thing is that we find a bimodal distribution like this in the mass, that is an effect of the bifurcation of the HR diagram. And that also is reflected in the log G or in the radius distribution. So, referring this bifurcation, one important thing that we have done is to make an easy exercise is to consider the objects here in the second bifurcation, second branch, these red points here, and we plot these points also in the color diagram. In the color diagram, DAs and DBs sequences are splitted, where here in the magnitude magnitude color diagram, they are not splitted, they are follow the same region. So what we observe is that at least 20 or 30%, or at most 40% of the objects could be considered DBs, in this case pure DBs stars, but most of them remains in the DA region. So this is one of the important results that we have derived. Secondly, the mass distribution. In this case, if we add, for example, mergers, white dwarf mergers, we can increase the number of massive objects, but we decrease the peak of single stars for a reasonable binary condition. But if we made the hypothesis that the mean mass of the mergers is strictly 0.8 with a 0.1 dispersion, then we obtain a more reasonable distribution according to the observed sample, but under this restriction that the merger mass should be 0.8. In other cases, it could help to explain this massive distribution here, but it's not perfectly explained. So, returning to our diagram, one of the things that we have done here is to ask how we can distinguish between the thin, thick, and halo population. In order to do this, we apply an artificial algorithm that is basically based on a random forest algorithm that use all these space dimensional, there are, I think, 10 variables, 10 dimensional space, using the information from our simulator in order to maximize the information that we can obtain from position, parallaxes, photometry, and also kinematical properties. And the results are these. The thin population is almost the 90% of the sample within 100 parsecs. A 10% is around the thick population, and we have identified around 95 candidates of halo white dwarfs that represent a 1%. This is the reduced proper motion diagram that we obtained. That is more or less what we expect, that halo stars are all stars and also high velocity stars. And here is, for example, the diagram when we plot the different population. But an important thing is that in this region, the ratio is higher. The ratio, for example, of thin Ds is around 32% instead of a 10%. So from this classification, we can derive, for example, the tangential velocity and splitting the objects that are in between, that with the reduced proper motion would be not possible to distinguish. In this case, our algorithm permits to distinguish the objects. We have derived an initial preliminary analysis of the scale height. And for the thin Ds, we derive a scale height of 200 parsecs, while for the thick Ds, almost remain constant, at least for 100 parsecs. Another interesting result is a preliminary white dwarf luminosity function. In this case, luminosity function is as a function of the magnitude, of the absolute magnitude. And we also observe that possible candidate halo stars are all stars. And as I said before, in the region of the drop-off or the cut-off of the luminosity function, we need to take into account the different populations. Okay, so in order to conclude, we have studied a 100 parsecs catalog that represents a volume-limited sample. In this region of temperature, we have the parameters, and we have observed that these parameters have an excess of massive stars that, in principle, are not attributable to the DA-DB's star. And possible white dwarf mergers could explain, but in certain conditions. And finally, we have also identified the different candidates for the thin, thick halo in these proportions in the 100 parsecs. And so in order to finish, I will like also to express my gratitude during these years working with Enrique. It has been an honor for me. As I said at the beginning, the code has 2 decades, and during this time I have been working with Enrique side by side. So it's very difficult to get an idea of his laws. It's very difficult, and well, and one of the things that Enrique uses in the sentence of his WhatsApp was a sentence in Latin that was multum in parvo, that means much in little, or something like this, that he likes because it was like a definition of a white dwarf. And well, I think Enrique, and probably you will agree, for much of us, it was much for many of us. And so that's all. Thank you very much.
Let's call up the next speaker and then we gather the questions. So it's Anna from Francesca Ava, and she's going to be talking about the mass distribution of accreting to white dwarfs from Gaia DR2.
Does this work? Use both of them. You can put it somewhere. So can I just use that one, or I know
This one is for the camera.
Oh, I see.
Okay.
And this
So
one I have to use it as well.
this one, can I stick it here?
Yeah. And this one here, you do that.
Oh, thank you very much. Yeah. So hello everyone, can you hear me? Is it? No? Is this on? Thank you. Can you hear me now? Yeah. So hi, my name is Anna. I'm from the University of Warwick, and today I'm going to talk about the mass of accreting white dwarf from Gaia DR2. So accreting white dwarf or cataclysmic variables are compact interacting binaries in which you have a white dwarf that is accreting from a Lie-type companion star. But today I'm not going to talk about CVs as such, but I will just focus onto the white dwarf. However, it's important to stress at this point that these systems are the best probe for compact binary evolution. And this is because in CVs, we can basically measure the physical parameters of the white dwarf. And since they are also numerous and bright, we can also carry out accurate binary population synthesis studies. And this is important because the same model that describes CV evolution applies to more complex systems like supernova 1A. And this is the reason why we should try to have an understanding as complete as possible of CV evolution. So what do we know about CVs? I don't know why it does that. So the theory tells us that CV white dwarf should be on average, well, that's the theory. The theory tells us that CV white dwarf should be on average as massive as single white dwarf. But what we observe is actually different. So we see that CV white dwarf are on average more massive than a single white dwarf. And in her paper from 2011, Monica showed that this is not related to an observational bias. And what she showed also is that the masses of CV white dwarf are on average higher than those of their detached progenitors. So does this mean that CV white dwarf grow in mass? Well, this is a question, and there is a long-standing debate on that. And this is, again, important in the framework of supernova 1A explosion. So what are the possible answers to this question? Well, of course, the first answer is no, because the model of nova explosion, which is the thermonuclear runaway on the white dwarf surface of the accreted material, predicts that the accreted material and part of the core of the white dwarf should be ejected during the explosion. And this should prevent the mass growth. However, we also have some recent numerical simulation that shows that after thousands of nova cycles, you have the inset of helium flashes. And what you get is that the mass grows up to the Chandrasekhar limit. So there is not a clear answer to this question yet. But we also have an alternative explanation. So basically, Matthias Schreiber proposed that you can have CVs hosting low mass white dwarf that are unstable for the accretion process. And these systems should merge, disappear from the CV population. And in this way, you can naturally explain why CV white dwarf seems to be more massive than single white dwarf. But I'm not going into detail because Monica will talk about that on Thursday. So the key point here is that we have observation and theory that are in disagreement. And we need to solve the discrepancy because we need to trust the model to be applied also to describe the pathway toward supernova 1A. But what if this discrepancy arises from systematics? Because if we look at Monica's samples, what we see is that 70%, which is this blue slice here in the pie chart, 70% of the system in Monica's sample, for them, the mass has been determined from the analysis of their eclipse light curve. So we have this method that we use to determine masses. It works, but since we have very little comparison, it's difficult to assess if systematics are affecting our result. So if we want to investigate the discrepancy between our models and the observation, what we need to do is to diversify the method used to measure CV masses and also to enlarge the sample of system of CV white dwarf that have an accurate mass determination so we can build a more significant statistical sample. But how do we measure masses of CV white dwarf? So if you have a single white dwarf, you take an optical spectrum, you feed the model, and you measure at the same time effective temperature and surface gravity. Well, you can just forget this method for CVs, because this is how their optical spectra look like. So you have these strong emission lines coming from the disk, and they fill the Balmer lines or completely hide the white dwarf. So you can't measure masses of CV white. In some cases you can, but quite often you can't, because they just look like that. And fortunately, the situation gets better in the ultraviolet, because at those wavelengths, you have that the contribution from the accretion disk and the secondary becomes basically negligible. And so the spectral energy distribution is dominated by the white dwarf. And so with the aim to study the physical parameters of CV white dwarf, in 2012, Boris got a large HSD program, and approved, and then during 120 orbits, he acquired ultraviolet spectroscopy for a sample of 31 CV white dwarf. And this is just 2 sample spectra from those observations. And you can see that the spectral appearance is dominated by the white dwarf, as you can see from the broad Lyman alpha absorption feature typical from a cold white dwarf. And we also have hotter system with this narrow Lyman alpha absorption and this steep blue continuum. However, there is an additional problem, because effective temperature and surface gravity correlate. Because once you have high temperature, you have a larger fraction of ionized hydrogen, and so you get narrower lines. But you can counterbalance this effect if you have larger masses, and so you get broader wings due to the pressure broadening. And this is an example for a CV in our HSD program. And so here it's always the same object, but I fitted the HSD spectrum assuming different masses. And you can see that there is a correlation. So if you have as you go for higher masses, you also get higher temperature. And all this model fit equally well the data. So it's very difficult to disentangle this degeneracy. And as you can guess from the title of my talk, you can break this degeneracy using Gaia. And this is possible because Gaia has provided parallaxes to the CV in our sample, so we have distances. And if you look at the ratio between what you observe in your model, this is basically related to the ratio between the radius of the white dwarf and the distance. So you take your spectrum, you fit it, you get your scaling factor, you know the distance, and basically you get the radius of the white dwarf. And then you assume a mass-radius relationship, and you obtain the mass of the white dwarf. And the main source of systematic in this approach is reddening, because if you have high reddening, you lose UV flux, so you get smaller scaling factor, smaller radius, and higher mass. So you need to be careful and take into account reddening when you fit UV spectra. So we use the 3D map for interstellar dust from Pansar and Tumas, and we fitted all the HSD spectra. And the mass distribution of CV white dwarf looks like that. So in blue, we have the data from Monica's paper in 2011. And this is the mass distribution from the Gaia data. And the two distributions are similar, because you can see that, again, we find that CV white dwarf are indeed more massive than single white dwarf. Although we find that the peak of our distribution is shifted toward higher masses than what was published in Monica's paper. And what is also interesting is that we have this tail down here, which suggests that there are actually helium core white dwarf also in CVs. So how does this result compare with other methods? So the last white dwarf workshop, I presented some dynamical masses. So basically for the CV in our sample, we also acquired phase resolved spectroscopic observation. And in 4 systems, we could identify metal lines from both the white dwarf and the secondary. So we took these metal lines and measured the radial velocity. And this is how the radial velocity curve looks like. From the radial velocity, you can measure the gravitational redshift of the white dwarf, and then you get an estimate of the mass. And within the uncertainties, the results from the dynamical measurements and the masses from Gaia are in good agreement. But the most interesting comparison, of course, is with masses determined from the eclipsing light curve. So in our sample, we had 1035. Its mass was determined by Litterfeld et al. In 2006 and is about 0.835. And with Gaia, we find 0.92. But again, we have systematics dominating, come from the reddening. And the two results are in agreement, again, within the uncertainties. And we do have more eclipsing system in our sample that we can use for comparison, but their spectra looks like that. And this is because these are high inclination systems, so basically we are looking toward the accretion disk. So we have this curtain of absorbing material that basically veil the white dwarf and give rise to all this absorbing feature. So it's not impossible to determine masses from this UV spectra. It's just because we have model for the curtains. The problem is that this model imply many additional free parameters. So it's something that needs to be done carefully, but we are working on that. And here are my conclusions. So we use Gaia and UV spectra to accurately measure the masses of CV white dwarf. We almost doubled the number of systems with an accurate mass determination. We confirm that CV white dwarf are, on average, more massive than single white dwarf, and we also have the first indication that CV could host also a helium core white dwarf. And once again, I want to highlight that this is important because if we understand the model of CV evolution, we can also trust the model to be applied to more complex systems, in particular to the pathway toward supernova 180 explosion. And thank you very much.
So I'm going to call the speakers back in and we'll do the session. And yeah, Patrick, no, not Patrick. Patrick, yeah. Yes. So do we have questions for the three speakers?
Let's go down here.
I was wondering if there's any physical motivation to the distinction you make between diffuse and massive decay. So you showed, for example, that their kinematics show they're in older populations. Is that arbitrary, or what? Is there some physics or astrophysics behind segregating?
It's two different populations. You can't see. I don't have the figure. There's a figure. The massive ones are descendant of the carbon atmosphere white dwarfs, and the cooler ones are simply normal dredge up from the core. So it's two different types. So one is due to mergers, and the other one is just.
No, I understand you showed that.
Okay.
How do you motivate their separation based on their mass?
Oh, well, when you look at the mass distribution, you have a peak, and then there's like a gap between 0.6 and 0.8. So I put it there. Yeah.
Yes. Okay. I understand that this DQ seems to be more massive, and maybe it is also very. Have you had a chance to look at magnetic white dwarfs, which are also more massive and?
There's a poster here by one of my students explaining all that. Yeah.
Okay, I'll have a look. And these are observational results.
We did a mass distribution of the magnetic white dwarfs.
Excellent.
Magnetic DH, yeah.
When you said that there was 95 white dwarfs, can you remind me, did you say that those were observed in DR2? Or that's predicted?
These are from DR2, yes.
Are you
For candidates.
Are those going to be published somewhere like what?
And we hope to publish this. We are now analyzing all these, the algorithms to distinguish them, and we have the idea to publish these white dwarfs, yes.
Looking forward to that.
The continuation really of this question. What about kinematical properties of magnetic white dwarfs? Are they old, older, or?
No, so they don't. Yeah, so if I look at the massive magnetic dwarfs, they don't seem to have an older population, so it's unlikely they are mergers. Or if they are mergers, it was before
both became white dwarfs.
Right, okay.
Anna, you found a UV white dwarf in a CV. This is awesome. Is there any way that we can, with other methods, double check the mass? And is there any way that this system stands out compared to the rest of the population?
So I do have additional data for the system, and I can see the secondary. So I was thinking to use, unfortunately I can't see metal lines from the white dwarf. So what I wanted to do is radial velocity from the secondary and then using the disk emission lines to have some constraint at least on the radial velocity of the white dwarf. And then compare the masses in this way.
And what is the period?
This is just below the period gap, like about 90, 100.
One last question.
It was shown several years ago that magnetic white dwarfs, because they are so massive, demand being formed in mergers. They never have a companion except for a very white companion.
Yeah, but what I say is if it was a merger plan, the merger happened early, right in the beginning, not after you have two full white dwarfs that merge.
Right. Two normal white dwarfs make a magnetic white dwarf.
No,
in
it
common
must happen before.
Or in the common envelope.
Yeah.
Let's thank our speakers again.
Our next speaker is Pierre-Emmanuel Tremblay, and he's going to be talking about the atmospheric parameters of white dwarfs from Gaia.
Hello, a bit of motivation for this. With Gaia masses for white dwarfs, we will now be able to plot them into a initial mass versus total age diagram. And we can also compare with the main sequence parameters for the same samples and then try to see if the wall of stellar evolution is consistent. And the starting point for that is having parameters for those white dwarfs. We have seen this morning that we now have 250,000 high confidence white dwarfs in Gaia that we can use, but only 10% of those currently have a spectroscopy, mostly from the SDSS. In the next decade, we will have at least 4 multi-fiber spectroscopic surveys that will follow up those Gaia white dwarfs. So we ought to have at least 50%, probably more of the Gaia white dwarfs, which will have spectroscopy. But in the next decade, if we still want to use the Gaia catalog, what we may have to do is to use photometric parameters and Gaia photometric parameters in particular. If we use Gaia data only, that's what we can do to get the parameters of these white dwarfs. We minimize 3 equations for the 3 Gaia filters, BP, RP, and G. And the observed Gaia flux is equal to the square of the parallax times the stellar flux. And the stellar flux is integrated through the Gaia filters and also through the full white dwarf surface. So it means that the input parameters are effective temperature, log G, and also the radius. There is a degeneracy between radius and log G. So we must assume a mass-radius relation when we fit Gaia data or photometry. And also there is a overlap between temperature and reddening. So we must assume a reddening as well. And in that case, we use the reddening maps of Schlegel and Schlafly, as has been done for SDSS. But we have made a new parameterization of the reddening versus distance using the empirical Gaia white dwarf cooling track. And we find a gas scale 8 of 200 parsec doing that. So here's what happens when we look, first of all, at the 20 parsec sample. The The Gaia parameters that we find are on the x-axis. That's the same axis at the bottom that at the top. And on the y-axis, this is the pre-Gaia literature value, mostly from photometric fits. And what we have done is only to use pure hydrogen, pure helium, or mixed atmosphere hydrogen-helium models. And we find a very small error bars with Gaia data alone, probably unrealistic small errors compared to systematics in the models. So then we can look at the difference between Gaia and previous observations. There is no obvious systematic. Gaia seems to work well within 20 parsec. And also, if we look at the spread in those parameters, we find a standard deviation of 0.1 dex in log G and 3% in effective temperature. The Gaia precision is likely to be better than that because some of the earlier parallax measurements were not as good as Gaia. The DZ and DQ white dwarfs are in orange. So because Gaia has extremely broad filters, using mixed or pure helium atmosphere works quite well for them. But Patrick mentioned the bifurcation problem in the explanation earlier, which is around 7,000 to 11,000, and we have very few local white dwarfs in this area. So this doesn't mean that Gaia with those model atmospheres will be perfect for every type of white dwarfs. Now, when we look at larger distances, we can look at the comparison between the Gaia dataset and other photometric datasets. So those are all photometric fits, no spectroscopy. I only use DA white dwarfs here to not have any residual model effects from some lines that we do not account for in the models. But the comparison here is between, well, here we don't see the y-axis, but this is the temperature from Penstars with greasy photometry versus Gaia. And on the right, this is SDSS photometry versus Gaia. And overall, the agreement is very good. We see no systematic offset. We conclude that Gaia and as well as Penstar and SDSS are well calibrated. We see no evidence of problem with those band passes. And reddening was also included in this comparison here. So this leads us to the Gaia Data Race 2 catalog of white dwarfs that was presented by Nicolas this morning. We have atmospheric parameters and masses for 250,000 of white dwarfs that are found in this catalog. Only a fraction of those have error bars that are comparable to typical spectroscopic parameters. Well, that's one reason why we need follow-up spectroscopy. But still, if you are looking at bright white dwarfs or white dwarfs within 200, 500 parsec, there's a significant amount of good precision Gaia fits in there. So overall, both we give both pure hydrogen and pure helium solutions, but for the whole catalog, 95% of the time, those are the same. The first reason is the very broad Gaia bandpasses. This is not very sensitive to the lines, but also at the fainter end, then the Gaia also data get less precise. And just one application of using the parameters in the catalog, we can look at the mass distribution of DA and DB white dwarfs. Those are all photometric fits. There's no spectroscopy in there apart from the selection of the samples. So on the left, those are DAs from Janinas 2011, DBs from Roland 2018. And on the right, this is the Gaia SDSS sample that Nicolas has discussed this morning. And all samples are similar because we use the same Gaia data. So this is not surprising, but there's definitively a difference between DAs and DBs. The DAs have a higher mass tail and a lower mass tail, while this is not seen for DBs. And Interestingly, the median mass is the same for both type of objects. The low mass tail is certainly from unresolved double degenerates, helium core white dwarfs. The higher mass tail has a few explanations. First of all, there's really a lack of massive DB white dwarfs seen in Gaia, and this is not new. Spectroscopic analysis have already shown this, but this is robustly confirmed from Gaia. And also, the explanation for that is not new. Already, we see a lack of massive DB white dwarfs in open clusters. So the explanation is very likely from single star evolution not forming thin hydrogen layers above 0.65 solar mass or so, and there's no convective mixing when those more massive white dwarfs are cooling. So the explanation was already in Caleri 2005, but it's nice that Gaia can recover that result nicely. Also, we see perhaps other substructure in the DA mass distribution. Some of it can be explained by the initial to final mass relation. Some of it can also be explained by crystallization, but we have an upcoming paper discussing those aspects. I want to also show what happens when we compare with spectroscopy. That would be a full talk, but I want to show what happens in particular for 3D spectroscopic parameters for DAs. So what we can do with Gaia is to use the spectroscopic solution, temperature log G, and then compute the absolute magnitude, and then compare with the apparent magnitude and predict a parallax. And for that, we have used the same DA models and the same fitting technique for the three samples I will show here. On the x-axis that is not shown, this is the temperature from 100,000 to about 5,000. And here I show the relative difference between Gaia parallax and spectroscopic predicted parallax. Objects that are at the bottom here are overluminous in Gaia. This is perhaps not obvious because parallax is not the most commonly used variable here, but the first observation is that there's no obvious signature from the mass-radius relation. If I was to use thin hydrogen layers for all those objects, I would pretty much obtain the same results. So it seems that either white dwarfs have a range of hydrogen mass layers, or that's, well, the random errors from Gaian spectroscopy are still too large to see those substructures. There's one thing that probably you have seen by now that is quite obvious. There seems to be an issue between 10,000 and 12,000. This really here corresponds to the classical IMAS problem for convective white dwarfs, and it seems that the three solutions do not fully correct for that problem. This is itself not totally new. Already when we published the first 3D corrections for DA white dwarfs, we could see a residual IMAS problem in the range from 10,000 to 12,000. So it means that Gaia is so precise, has so many objects that now it becomes very obvious, but I don't think we should worry too much about that. So we'll leave the conclusions there, and thank you.
So our next speaker is, I don't know how to pronounce Renee Wall. It's easy, you know?
Yeah.
The Galaxy absolute calibration and extinction coefficients based on white dwarfs.
There we go. Clicker. For my slides to come. All right. Hello, everyone. Again, I'm Renee Wall, and I'll be talking to you about Galaxy. So the first question that white dwarf people are going to ask is, why should we care about a UV Galaxy survey? But there are a couple things that you can find using UV. if you have a white dwarf with a UV flux that's significantly larger than model predictions, this could indicate that you have a binary system where one white dwarf is a lot hotter than the other. If you have a significantly lower UV flux than expected, then this could indicate that you have a lot of metals in the atmosphere. So that's what we want to eventually look at, but before we do that, we have to do calibrations. Why GALEX needs calibrations? There were two types of nonlinearity that are present in GALEX data. The first is global nonlinearity. This was due entirely to detector electronics, so it was pretty easily characterized and corrected for. The second type of nonlinearity is local nonlinearity, and this occurred only near bright sources where the CCD is saturated. So as we all know, saturation is hard to deal with. So in 2007, Morrissey et al. Made the first attempt at an empirical correction for local nonlinearity. And is this, okay. So on the y-axis is measured rate of photons per second. X-axis is the predicted rate. The dotted black line is the one-to-one correlation. And what they've done is they fitted a second-degree polynomial to both their FUV and NUV data and said that this was a preliminary correction for local nonlinearity. But as you see, they have a very small sample size, so it was important to go back and do this with a larger sample, which was done in 2014 by Camerata and Holberg. Again, we have our dotted black line is the one-to-one, and now we're working in magnitudes instead of photons. And the black solid line is the new quadratic, not quadratic, yes? I'm sorry, I'm panicking. Second degree polynomial fit. And they postulate that their new linearity correction should hold until about 20th magnitude, but their faintest star is about 17.5. So we should revisit this with fainter stars to make sure everything's okay. As for the extinction coefficient, there's a wide range of values that were reported in the literature. I have an example of model predictions from Bianchi in 2011. They report RFUV between 8 and 12.7 and NUV between 8 and 8.1. And to date that I know of, there's only one paper that's gone and empirically derived extinction coefficients for GALEX. And this was Yuan et al. In 2013. And they have an RFUV of 4.37 to 4.89, and NUV from 7.06 to 7.24. So the NUV value that they derive is not horribly far from model prediction, so that seems okay, but clearly there's something funny going on with the FUV. This becomes pretty clear when you look at their data. The top two panels are for NUV, bottom two for FUV. And what they did is they bin their data and they fit a line to the binned data. And in the top, there's an obvious trend. So this works pretty well. But for the FUV, there's no obvious trend in this data. So by binning it, they created an artificial trend, which is why their values are off. So we need to redo this. Moving into my work, I selected all spectroscopically confirmed DA white dwarfs from SDSS with signal to noise greater than 20. I cross-referenced this initial sample with GALEX, and once Gaia came out, I cross-referenced that again with Gaia and selected all of the stars with 5 sigma significant parallaxes, leaving me a final sample of 2,870 stars. So these stars we derived new T-effective and log Gs using updated models. Then from those, we get our absolute magnitudes based on the models. For linearity correction, I select all stars within 100 parsecs. And my sample is between 14 and 26 mag. So I combine this with Cameron and Holberg's sample because they have a lot more brighter stars. So we have more full coverage. Here are my results. Observed magnitude, y-axis, synthetic magnitude on the x. Our dashed black line is the one-to-one. And this dotted red line is from Cameron and Holberg. The solid red line is our new fit. As you can see, they postulated it should hold about to 20th magnitude, and it clearly doesn't. So it's a good thing that we've revisited this. But local nonlinearity only occurred near bright sources. We need to define what does bright mean. So what I did is I calculated the point at which our new fit crossed the one-to-one line. For the FUV, this was about 16.5, and in UV, it was 16.3. And above that point, there's not a statistically significant difference between our fit and the one-to-one line. So you only need to apply a linearity correction to magnitudes brighter than those. So, yay, we have the linearity correction. So now we can move on to the extinction coefficients. I selected all stars with Gaia distances greater than 250 parsecs, applied the linearity correction to the brighter stars, and then for each individual star, I calculated our FUV and our NUV. I took a weighted average of both of those, which gives me final value for the new RFUV of 10.19 plus or minus 12, and NUV 7.81 plus or minus 11. So see these in action on the left for you guys here. We have the 250 parsec and beyond data without an extinction correction. And then I apply our extinction coefficient correction, and everything moves down to the one-to-one line, as you would hope. These red squares are 5 sigma outliers, so these are the possibly interesting things that I'll be looking at later. See the same trend with the NUV. Again, without any extinction correction, as you would expect, everything's above the one-to-one line. We apply our new correction, and everything is now hugging the one-to-one line, which is what we like to see. So, in conclusion, we have derived, well, found, I don't know, new linearity corrections for Galax data. The range over which those corrections are necessary, and the new empirical extinction coefficients. And I'm done.
Yeah, well, come back. Right. Did you leave? Do we have questions about Gaia and about Galax?
That's to Renee. Sometimes you have weird Galax magnitudes without any obvious reason, because sometimes the source is close to the edge of the detector also. And if you have quite often you have several measurements which are discrepant by more than the uncertainty. How do you deal with that?
So I don't think I actually looked for edge effects. I will go back and do that. But for the multiple different values, I just took the weighted average and used that. What I did.
for René again. Your plots are not anymore, but there seemed to be an effect, sort of an overcorrection for some of the brighter absolute magnitudes that you had. Are you tackling that in some way? So yes, everything was hugging the one line much better, but at the bright end, you see.
Yeah, I know what you're talking about, and I don't think that we've actually quite figured out what's going on there. That's definitely something we want to pin down.
Oh, I don't know. Okay. Who? Me? Oh. Sorry.
Raise your hands.
But I'm not tall enough. So it's red as well. How do your extinction coefficients compare with those of U1? And how do you explain the difference? I think there's a huge difference between all of them.
Yeah, so for the NUV, there's not really a large difference.
Yeah.
But for the FUV, we would expect that there's going to be hopefully a big difference since their value was so far off. And also we're using a totally different method to find it. They use the standard pair method with mainly FGK dwarves. So we're doing it with DA white dwarves, so that's also probably going to cause a slight difference.
Yeah, but so you think it's just a difference in the method? My question is, which one should I use from now on?
Well, I think Ewan et al. Cautioned against using their FUV value because they realized that it was bad, so don't use that one.
Thanks. I have a question for Emmanuel.
Just a general question. You said that from the DB population, you explained the lack of DBs through a lack of mixing. I was wondering if you think that the population that is born DB is too small to actually produce a visible effect.
Just trying to understand fully. We have quite a bit of DBs in DAs in Gaia, so it shouldn't be an issue with the size of the populations. I mean, if we don't see now massive helium atmospheres, not only DBs, but in Nicolas' talk, we could also see that there was a lack of massive DC, DZ, DQs at the fainter end. So those objects, if they have thin hydrogen layers, if the DAs had thin hydrogen layers, should have mixed up and created massive helium atmosphere white dwarfs.
Okay, but you also have the ones that are born helium atmosphere that somehow consume all the hydrogen.
Those also should be rare at higher mass, otherwise we would see them in Gaia.
Okay.
Okay. What was the mass or log G difference in your bump around 10 to 12,000? How large was it?
Well, Gaia doesn't give directly the log G, so I cannot code a mass offset or a log G offset because some of it could also be due to temperature offset. The effect on the radius and luminosity is relatively large. When we look at the mass distribution, nothing has changed. The spectroscopic masses are still more or less in agreement with their evolution with 3D models. There's a residual bump of the order of 7% in the masses. Gaia might be a bit larger than that on the masses, but we cannot fully isolate the masses from Gaia.
Any more questions? One more. Come on.
So this question could actually relate to both talks. So both of you talk about applying extinction corrections and retinue corrections in the results or measuring these, but you just apply these uniformly across all white dwarfs of broad temperature ranges. Because a lot of these extinction corrections are across relatively broad bands, and so typically extinction will be greater in bluer temperatures, bluer edges of these bands, hence hotter white dwarfs
will have additional extinction relative to cooler white dwarfs. And this can be an important correction in some contexts.
Yes. Now that you said that, I totally agree. I haven't really come across people doing something like that in the
Well, a lot of
literature.
people would ignore it, but they shouldn't.
Yeah. Yeah, because usually you get some number, some R value, and then you just, if it's beyond 250 parsecs, you just apply that. And between 100 and 250, you do some worrying about that, but otherwise that's a good point. Basically, is my answer to your question.
Well, I can say that in our case, we would welcome full 3D rendering maps. We have tried with some of those, but if you have something at 200 parsecs, sometimes at a specific line of sight, you don't have the detailed rendering value for those 3D maps. But we work with the reddening versus distance parameterization and also reddening versus wavelength for the different filters that we use, and that's the best we can do right now. Okay.
Let's thank our speakers again. Our next speaker is Jing Cheng-gu, and he's going to talk to us about the white dwarfs in Lamos DR5.
Hi everyone. I'm Jin Cheng-Guo from Peking University. I'm a postdoc now, and I'm here delighted to introduce you with Thinker white dwarfs discovered in Lamos data release 5. And first, the overwhelming majority of all stars end their lives as white dwarfs. So it is believed that 97% of the stars in the galaxy will eventually evolve to white dwarfs. So we have those significant perspective that we have to. It is important to study the white dwarfs. So I will just skip that. And during last 3 decades, efforts have been made to build large samples of stars, especially those McCook and Cyan, the large samples from SDSS, and also the Montreal white dwarf catalog. I just missed here. So Lamos, just a little reminder, Lamos is a 4-meter telescope with 4,000 fibers built in China. It was it's a spectroscopy survey, and it's just ended its first phase during the past 5 years. So in those 5 years, a lot of people have worked on the Lamos white dwarfs, and basically we just end up with no less than, say, 3,000 white dwarfs. And here I'm trying to discover more from the newest data release. So first, I'm gonna talk about the DA white dwarf selection. So basically, I'm quite I choose to believe the pipeline is solid, so we just rely on the pipeline and choose the spectra obtained in data release 3, 4, and 5 because we have already published one paper on data release 2. And we choose the subclass of white dwarf magnetic carbon white dwarf and double stars. Those end up with about 7,000 candidates. And next, we talk about the DB white dwarf selection, and we are trying something new. So we tend to the machine learning, and we finally, after a comparison with other different algorithms, we choose the random forest. And this is a result of a little test we did. And basically, we just cross-match data release 5 with Sinbad. We find about 178 common sources. And among these sources, 150 are classified as unknowns, and most of them are low signal to noise ratio. So we selected those with G-band signal to noise ratio greater than 10 as our training sample, and that is 45 dB white dwarfs from Sinbad identification, and we resulted in more than 10,000 candidates, and we think this number is quite large, and maybe it's needed further improvement on the algorithm. And after that, we did a visually inspection for the DA white dwarf candidates. We end up with a little less than 2,000 DA white dwarfs, and for DB white dwarfs, we only find 150 DB white dwarfs. And after cross matching with previous catalogs, we found almost 400 DA white dwarfs are new, and 46 DB white dwarfs are new. And after that, we are trying to determine the parameters. Just for DA white dwarfs, we select only signal to noise ratio greater than 10. And first we got we fit the absorption lines profile and got the effective temperature and surface gravity. And through that, we can further determine the mass and the cooling time. And this is a distribution of the parameters we just determined, and we also provided the new Gaia DR2 distance. And here is a comparison between our sample and SDSS sample. We can see it's quite consistent. And for DB white dwarf, we also try to determine their parameters, and we fit the whole spectra to get the surface gravity and the effective temperature. And also we obtained the mass and the cooling time. So here is the distribution of the parameters and the comparison. Also, after the first phase of Lamost, and it's ended last year. So started from last year and until this year, summertime. It's 1 year of transition and test. So next phase, we will carry out the medium resolution observations during the bright nights. And also we also have low resolution observations during dark nights. So for the medium resolution observation, the spectral resolution will increase to 7,000, and but we only can do it brighter than 15 magnitudes, and the RV accuracy will less than 1 kilometer per second. So this is I think this is an opportunity for us to just propose for more white dwarf observation, because compared to SDSS, we only discovered a few thousand white dwarfs in over 10 million observed spectrum. So next, we selected much more candidates, white dwarf candidates, through the reduced probe motion and also Gaia. So we'd like to propose those candidates to observe at the second phase of LAMOS, and I hope it can be approved. Yeah, and this is my introduction. Yes, thank you.
Thank you. And our last speaker of this one is Edwin, and he's going to be talking about the white dwarf and super dwarf stars in the slow for data release.
So there was no optical data in data release 13 of FDS. So that's the reason we moved from 12 to 14, sorry, 12 to 14. So sorry, my talk has many collaborators because we looked at many stars. So it started with the 4 million spectra of data release 14, which includes all the previous data. And in the past, up to data release 14, we were concentrating especially in the color selection, which selected the brighter and hotter stars. And because of that, when we did the simulation population synthesis, we noticed that most of the white dwarfs that we have published up to now are younger than 2 giga years. So we are missing all the older white dwarfs. So for the data release 14, our selection was on proper motion. Well, the initial selection was on top of everything that we had done before, which is the color selection, the pipeline classification, and the automated search. We did an additional criteria, which is to look at every spectra that has 3 sigma proper motion larger than 20 milliards seconds. And that was 259,000 spectra. So we started the visual inspection of all these objects to classify. So we first eliminated all the main sequence stars up to spectral type of F. And then we were left with about 120,000 spectra, and we did the visual inspection. So that's the reason we have this large table with many different types. Okay, so we have 15,590 DAs. They are not, only half of them are new. because we did everything that had proper motion. So not only known or not known, we did everything. So we have 15,509 DAs, and of the DAs, we have different spectral types, and especially important are the DABs, DAOs, and DA helium, because they show that there is mixing, spectral mixing, so there is convection mixing that is changing the spectral classification with temperature. For the dBs, we also have dBAs and everything else. So it's very important to take account of the spectral mixing, and I think we now have a large selection. Most of the talks up to now always refer to the spectral selection, because when you select the Gaia colors, it's necessary to know where the white dwarfs are, and they are not at the white dwarf cooling only. So when this plot is for the temperature of our new 15,000 DAs, and we have finally reached the end around 5,000 degrees for spectral selection, not photometric selection. Okay, so we know the stars are DAs, and these are only the pure DAs, no mixed types. So we have now finally reached. So with the selection, we were able to go to 5,000 degrees. The fainter stars, if they are, the higher masses are certainly fainter than 5,000 degrees. The higher masses DAs are fainter, are cooler than 5,000 degrees, but they do not show spectra with signal to noise larger than 3 in the SDSS because of the faintness. Their intrinsic faintness is smaller radius. So even for HST in the globular clusters, we saw that the fainter stars are below 28th magnitude for the closest cluster. So very hard to look at the very faint white dwarfs. Gaia has done some, and we'll talk about it in a minute. Okay, so this, again, is just for the DAs, and in this density diagram, I show the log G versus temperature, and what's important here is the change of the number of stars, or the masses, or log G of the stars for the lower temperatures. So when we did now a mass, this is just normal number, is not corrected by volume yet, this one. So these are the mass distribution for the DAs. So in black, I have the total mass, and I have in blue the stars hotter than 10,000 degrees, which show the normal peak around 0.6 solar mass. But we have also the low temperature DAs on the bottom here. This number is smaller. These are signal to noise above 10. That's one of the reasons that the number is smaller, is because of we are selecting only the brighter one, although the low masses are brighter than the higher masses, so it compensates a little bit with temperature. But you can see that the mass distribution for the white dwarfs cooler than 10,000 degrees is very different, and the mean mass is 0.52, which is in agreement with what Jean Lieber told me 10 years ago in a white dwarf conference, that in the clusters, the mean mass for the white dwarfs are around 0.5 and 0.52, the mean mass, not for the higher mass. Fabiola is complaining because she calculated the mass, but it is. So for the dBs, this is only 805 dBs with signal to noise above 10. And again, this is not for all the dBs that we have found in SDSS. It's for this selection of DR14. And for stars cooler than 16,000, we see the change in log G. And There'll be talks tomorrow by Mark on the experimental measurements of the helium lines. There will be a talk by Elena on the 3D simulation, because these are not corrected by 3D. But again, one of the main problems is not the line profiles, is the mixing with hydrogen. So like Patrick mentioned, so for the cooler stars when the convection zone goes deep, or if there is a very thin hydrogen layer on top, then, so I'm hoping that with these talks, and that after we correct it by 3D, that we be able to at least discard or correct it, what is the effect of 3D, but there are more effects than only the 3D and the line profiles that the experiments will show. So 3 months ago, Gaia was released, and this is the plot of all the 90 million 10 sigma and selected by all the parameters that you heard from Stefan this morning. And I have plotted on top of the Gaia stars. So the 10 sigma includes the white dwarfs and the main sequence, but in very tiny points, so that the stars from DR14 will not overlap or will not hide. And you can see in blue here are the DAs, and the DAs and the DBs and the DCs are not restricted to what we call the white dwarf cooling. Okay, so that's a problem. There are problems with the data, for sure, like Stefan told us. So in 2020, when we have better Gaia colors and parallaxes, the picture might change. I don't think it will change from DAs all the way up there. Okay, and the bridge between the main sequence and the white dwarf cooling sequence, if you look at all the plots from Gaia, you always see that bridge, and you can cut, but I don't think you should cut. I think we have to take spectra like we did and look at the spectra, and most of these, well, there are so many colors here that I am colorblind, I cannot see, but but I have in green the DAs, in green the DBs, in a different green the DCs, a different green the Vs, and so on. And in yellow I have the DQs, and the DQs, like Patrick showed also, or Pierre-Emmanuel, also go into the lower part, where the massive part of the DA should be. So there are also the lines, the predicted colors. So there are many different objects here. And I have also overplotted on the same diagram the location of the DAVs, the DBVs. So, okay. So this is the same plot with just the cut into the DAs, and there are the subdwarfs over there. The last point that I want to mention is, finally with Gaia, we could do a photometric selection, a photometric determination of the masses for the DCs. So we did, this is the work by Gustavo Rique, and so the mass distributions are spectroscopically selected classes, but photometrically determined masses. So the Gaia colors and the distance. And you can see on the plot, the original plot and the corrected by volume, that the DCs have a different mass distribution than DAs and DBs. So I will stop here and let you ask questions. You shook your head.
So do we have questions, Boris? Yes.
totally new white dwarfs have been found in data release 13 and 14 compared to the previous ones? Because Sloan has become extremely good at excluding single white dwarfs.
Yes, it was on my big slide with the table. It's now a total of 40,000. So the total is 40,000.
How many new ones compared? How many new ones compared to your 12? Because
9,000.
I'm surprised because Sloan has developed very efficient strategies to remove single white dwarfs by including wise colors.
Yes, no, what Boris is saying is the selection mechanism by FDSS of, I think of what he's saying.
Of the things they take spectrum.
Yeah, the things that they take spectrum. So they are not pre-selecting white dwarfs. So the white dwarfs come only accidentally, but they're still, okay. And then I have to correct my phrase. There are only 6% of the white dwarfs that are in the new data release 14 data. The reason I have 9,000 is because we looked at all the data and looking for the cool white dwarfs that we had missed before. So only, yes, on the new data, only they are not observing white dwarfs if they can. So the selection mechanism is hard.
I would like to ask a question to Kitchen. So what is the completeness of your white dwarf catalog?
I cannot specifically answer that question because I just tend to believe the pipeline.
So you only base your DA catalog on the pipeline, on the white dwarf?
Yeah, for the DA.
Pipeline on white dwarfs.
Yeah, for DA white dwarfs, I only choose those classified as white dwarfs.
Use your random forest or any other techniques to
find
more DAs?
You're gonna find one, right?
Yeah, I have tried several methods in our previous paper, but it's only we only find more other types of white dwarfs. It's for the DA white dwarfs. I think the pipeline, based on our experience, the DA white dwarf is sufficient enough just to choose from the pipeline.
May I comment on this? I think we need to do, the whole community need to do a search of white dwarfs in the Lamos data. There are 8 million spectra. The data is much harder to work than FDSS, but I think the visual inspection has to be done, like he said, when you include when he did the random forest, there are a few 10,000 of spectra to look, and of those a few 10,000, you get, he got like 1,000, but there are many more there for sure, and we have to look at. And I have wanted to look, I have started to look, but to look at 8 million spectra needs time.
I have a question for Kaplan.
Yep.
You said that the initial selection you done was based on the proper motion?
Yes, plus. I did the color selection, we did the color selection. So Ingrid looked at 78,000 by color selection, plus the proper motion.
Were these proper motions from Sloan, the Sloan given proper motions?
Yes, but
so there are a few percent of objects with spectrum Sloan that do not have proper motions.
Right.
About 5% of known white balls do not have a measured proper motion.
Right.
Spectra do not have a proper motion.
Right.
Did you include this back?
Well, I did not redo all the 20,000 white dwarfs that we had done. Okay, so those were not selected by proper motion. We only, in addition to the color selection for the new ones, the automated spectral feed, in addition to those, we did the proper motion. And then I went back to Gaia, after Gaia, I went back and looked at the ones that are in the white dwarf Coulomb sequence and had spectra. So I compared to your table, and we are very similar, but I have stars that you don't, and you probably, no, I don't know that. Okay. Lilia.
slides you put up, you showed there are about 16,000 DIY dwarfs and 600 only binaries within dwarfs. That's a very small number.
Well, for this selection with proper motion, yes, but if you include the 600 that we had found before, it's about 1,000. So it's about 1,000, and well, at the signal to noise of the majority of spectra, it's hard to find the small magnetic field. So.
Thinking about magnetic,
Okay.
I was just thinking about incidence of binarity among white
Oh, binary, sorry.
Yeah,
Okay.
binary.
Binary, yes. Yeah, well, the catalog by Alberto has like 25, this Alberto, right in front of you. This guy, this Alberto, has 2,500. And so we did, with the many of the binaries don't have measured proper motion because they are binaries. So that will be corrected or dealt with in the next data release from Gaia. So that we will certainly improve. But my worry right now is the binaries are in the region that everybody is not calling a white dwarf cooling sequence. So it will not be taking spectra.
Thank you.
Let's thank our speakers again. Lunch will be served at the other room over there in Santa Rita. As you probably noticed, these doors are not open. I cannot personally guarantee that nobody else is coming, but I haven't seen any traffic.
Let's leave this.
Anybody else who's
There's just somebody. I'm gonna get some food before people get it and come back.
Okay. Yeah. So we come back at 2:30 then. Okay?
Sorry? Yeah, right. Yeah. There's a pawn shop just a few blocks down there. Truck? Yes, awesome. It's going to be a profitable trip.